Regional meeting and symposium. As we all know, the mobility electricity revolution is really this massive 21st century economic shift. This is happening as we speak, and it's going to only grow. About 1/3 of the primary global energy powers transportation, and this is anticipated that almost all of this will eventually shift to electricity production and delivery. The Bureau of Transportation Statistics estimates more than 10 million total US jobs in transportation and related industry, and again, we really expect that it's going to grow. So this meeting is really a conversation about this paradigm shift that we are living through. We'll talk about critical challenges in the transformation of our national transportation system to low-carbon electrical energy. Our featured speakers today will talk about challenges and opportunities and their visionary work, ranging from zero-emission aircraft and transformative off-road vehicles to mineral resources needs, cybersecurity, and infrastructure impact. The meeting is co-hosted by the National Academy of Engineering, the National Science Foundation, Power Optimization of Electrothermal System, POETS, which is an ERC here in its 8th or 9th year now, the Illinois Center for Transportation, the Granger College of Engineering, the Granger Lecture Series, the Tycho Sinner Lecture Series, the Kent Seminar Series in Transportation, and the Materials Research Lab Distinguished Lecture Series. So we really hope this will be a very exciting and a very information-rich event for you, and lots of discussions, we hope. And before we go any further, I really would like to thank Professor Phil Klein and the committee that really organized this great event together. So Phil, I think you should stand and just get an applause now. And then the entire committee that was working with Phil and our terrific staff members that are here, making sure everything works well. And Phil will come back here. I'm going to introduce him again. But before I go any further, at this time, I'd like to introduce President Tim Killeen, President of the University of Illinois System, and also a member of National Academy of Engineering, and a faculty member in Electrical and Computer Engineering, to the podium.
Thank you, Rashid, Dean Bashir. I also want to welcome you all to this regional meeting of the National Academy of Engineering here at the University of Illinois, Urbana-Champaign, and thanks as well to Chancellor Jones, who's here somewhere, and Vice Chancellor Susan Martinez, and I believe we're going to hear from both of you. Obviously Phil Klein and your team has been amazing to put this all together, as well as Dean Bashir as well and his team as the local hosts. I'm also delighted to see all of you here, and particularly our NAE president, John Anderson, and a distinguished alum, current president of the National Academy of Engineering, got his PhD at UIUC, and NAE Chief Executive Al Romig, who I'd like to give an honorary alumship to, if that's possible. I think there may be some things that presidents can do once in a while. I also want to start by remembering 4 absolutely towering engineers in the engineering community who unfortunately passed away fairly recently. All were distinguished members of the NAE and legends who had work that had an outside impact on the academy, industry, and the lives of all of us. Gordon Moore, as you know, the co-founder and later CEO and chairman at Intel, who saw decades ago that technological advances would only accelerate, sadly died last month. And Moore's law, as it's known, could not have been more prescient. The 3 other giants I'm speaking of all called the University of Illinois Urbana-Champaign home. And Bill Wolf, who was the president of the NAE for 11 years, I learned just an hour or so ago, got his physics bachelor's degree here at UIUC. And I know him, amongst other things, for his definition of how people should collaborate, coining the term collaboratory as a place where people can come together, aided by digital means, cutting across boundaries of space and time. And then, of course, Professors Nick Holoniak and Peter Sauer passed away after long and extraordinarily productive and influential careers and lives. Nick Holoniak was elected to the NAE for his contributions to the development of semiconductor-controlled rectifiers, diode lasers, and of course, the LED that we see literally everywhere. Pete Sauer was elected to the NAE for contributions to electric power and energy systems, a major emphasis of today's symposium. We will miss them all, but also remember them well for the many ways they touched and helped shape modern life. And that's what the NAE is all about, having an impact on modern life and society. The advances that these visionaries made are a major part of the reason that NAE exists. It seeks to provide a wise guiding hand in research and public policy around major shifts in technology. And as you all know, these shifts are coming at such a rapid pace in our world and are so interconnected that we live and we work in a constant, broad state of flux. And of course, we're in Illinois, as you know, and we take advantage and take ownership of everything Abraham Lincoln ever said, might have said, wanted to say, but never got around to saying. And of course, he started the national academies with the concept that intellectual heft can help shape the evolution of the United States in directions that will build and create prosperity and also serve the national security needs. So in that context, we're happy to be in Illinois, we always are, and we take advantage of Abraham Lincoln's work. Change is driven by innovation, by the spark that fires an idea, but necessity can also drive change, as we all saw with the COVID period that we've just come out of. Nick Holoniak went to work for the Illinois Central Railroad as a teenager laying ties. I didn't know that until I did some research. As the first in his family to receive a formal education, he knew after a 30-hour shift repairing damage to a rail line from a flood that he badly needed to find a different intellectual path, and boy did he. All that he created, he once told a reporter, owed its existence in some small way to the demanding workload thrust upon downstate railroad crews decades ago. Right now, the urgent need to reduce our own impact on the planet while continuing to move more people and things from here to there is driving a revolution in real time, a revolution in electric transportation. It promises more disruption in transport than we have seen for a century. Industry projections that electric vehicles could account for a quarter to almost a third of new car sales in the US by 2030 have manufacturers all around the world pushing ahead with new products and plans for more and more and access to the market share. Electric power is becoming an option in agricultural equipment, and aerospace companies are testing prototypes. Economists estimate that the direct market impact of electric transportation will be more than $1.3 trillion in the US by 2030. That's a huge number. So the global market impact and the benefits from reduced pollution and carbon reduction are far higher than that. We can already feel the impact in Illinois, right here. Just an hour up Interstate 74 from us, Rivian employs about 6,000 people at its truck plant, churning out the Amazon trucks that you see pretty much everywhere. I'd just like to say that in Rivian, every day they tested for COVID using the UIUC saliva test developed right here as a great example of industry academic partnerships. That's why it was able to stay open. Everybody there had to test regularly. Then 100 miles north in Joliet, Lion Electric has built a manufacturing plant for electric buses. The first was produced just last November. So we're in the bus arena as well. Illinois and the Great Lakes can and should be a real epicenter for the EV revolution. And let me remind you of some of the reasons, I think, for that statement. This region is already the nation's key transportation hub. The transportation infrastructure in and around Chicago is massive and absolutely vital to the rest of the country. That centrality provides some of the need I mentioned that helps drive a revolution. People, agricultural products, the raw material produced by mining, heavy equipment used in mining and construction, all move constantly through this dynamic hub at incredible scale. And don't forget that Illinois and the Chicago region also serve as the long-term base for many in the transportation industry: Boeing, Navistar, GE Transportation, the primary American offices for Nissan, Continental Automotive, Hyundai, and many, many dozens more. We also have the engineering and research muscle at scale with excellence of a number of universities, including, of course, UIUC, and other institutions in the neighborhood, including DOE National Labs. The Granger College of Engineering right here at UIC, as you know, is a powerhouse with a long, storied history of innovation around transportation, logistics, power systems, which was Pete Sauer's great expertise, and more. Argonne National Lab nearby offers expertise in advanced battery research as well that we're paying close attention to, and University of Illinois Chicago is a major partner for. A key ingredient in our secret sauce here is our state leadership and its deep understanding of the need before us, as well as the opportunities. So alignment with the state leadership is there and pivotally important as we grasp the opportunities into the future. Our governor, J.B. Pritzker, has made EV production a major priority in the state of Illinois. In 2021, he signed the Reimagining Electric Vehicles in Illinois Act into law to add incentives for Illinois' growing electric vehicle production capacity. So the stage is set for Illinois and the Great Lakes region to be leadership and an important transportation node for the country, but even more important transportation node for the country. This afternoon and on Wednesday, during the Industry and Policy Forum, you will have a chance to hear about and discuss some of the key questions we face. I'm personally, as a member of the NAE, I'm personally so excited to have you all here. We're moving in the direction of informing public policy at scale in an important dynamic period of time. I'm energized to be a chance to be part of this gathering. I hope all of you are as well. And now, after my short but restrained comments, I assure you I could go on for longer, I'm honored to introduce the President of the National Academy of Engineering, John Anderson. John has been president since 2019, and I've already mentioned he's a graduate of UIUC, earning his PhD in chemical engineering here. I know there's some chemical engineers in the audience, and that is a powerhouse of a department, we all know. He's held leadership and faculty roles at a number of universities, including serving as president of the Illinois Institute of Technology from 2007 to 2015, and he's dynamically leading the NAE into its next decades. Please help me welcome John to the microphone.
Well, it's good to be back. Brings back memories. As some faculty have said, this is the scene of my crimes when I was young. And I certainly not only worked hard here, as you're expected to work hard, I had a lot of fun as well. There's a lot of places in Champaign-Urbana, and Green Street was a common endpoint for us in the evening after working till midnight or whatever in the labs. I visited some labs today. I can't believe the advances have been made, and the tedium is gone from working in some of these wet labs, and you can now concentrate on being creative. It's fantastic. A special thanks here to the University of Illinois for organizing and hosting this regional meeting on the Mobility Electrification Revolution. It's really exciting to see this. I'd also like to thank the many organizations that are co-hosting this regional meeting. The Engineering Research Center, funded by the National Science Foundation, called Power Optimization of Electrothermal Systems, POETS. That's the best acronym I've ever heard, especially from engineers. So wonderful, POETS. The Illinois Center for Transportation, the Granger College of Engineering, the Granger Lecture Series, the Tycho Center Lecture Series, the Kent Seminar Series in Transportation, and the MRL Distinguished Lecture Series. I should say, when I was a student, the MRL, Material Research Lab, was a big deal, and I used it. They did some work for me on my some of the equipment I had. So this is certainly a great team effort. And again, I want to also thank Phil Krein. He put a lot of work into this to make it what it is, and did an exceptional job. So thank you, Philip, and the staff, especially the staff, for doing this. Regional meetings of the National Academy of Engineering are held for basically three purposes. One is to raise the visibility of engineering and the National Academy of Engineering. Secondly, to connect the officers and staff of the National Academy of Engineering with members. And thirdly, showcase the outstanding work being done by the host, in this case, the University of Illinois, and in engineering. The first regional meetings were launched in the year 2000. And here we are 23 years later, and the value of these events, especially post-COVID, are even more important than they were before. The benefits of meeting in person, sharing information, and networking on both professional and a personal level cannot be understated. We plan 4 regional meetings per year, the National Academy of Engineering. For 2023, the first meeting was held at Illumina and in University of California, San Diego. And we have 2 more, this is the second meeting. We have 2 more regional meetings planned this month, one at the University of Central Florida, and the final one at Lincoln Laboratories up in Boston. So it's a great time to be an engineer. And I'm addressing the young people out there because the future is yours. And I can't think of a better, no matter what you want to do, I can't think of a better opportunity. So to kind of highlight this, I want to show a video, which is the most important part of this talk. How do I do that? The volume's important. No dancing allowed, though. Oh, no sound. We got to see it. Whoops. I'm a chemical engineer, so I can't help too much on this one. There we go. There we are. So I'm interested in what the younger people out there, my definition of younger changes with time, but who the younger people out there think about the video and ways we could do it. We're going to be doing more of this and try to make engineering, the visibility of engineering grow here. Engineers work on a lot of challenges, from climate change, pandemics, space travel, everything in between, and we create products and systems that will benefit society and often not anticipated by society. Too often I hear engineering expressed as we solve problems, we're problem solvers. But we do more than that. We create things that we didn't even know we needed. So yesterday was the 50th anniversary of the first cell phone call made in the United States. A man named Marty Cooper made that call to AT&T from a brick phone that weighed 26 ounces, handheld. And he was the chief engineer for this project at Motorola. And a lot of things had to happen for cell phones. It took another 10 years to get a cell phone that weighed only about 4 or 5 ounces to get in your hand, because there had to be a lot of advances in microelectronics and whatever. So we celebrate April 3rd, 1973 as the beginning of the cell phone. But who said back then that we needed a cell phone? It wasn't on the mind of everybody. Another example is DNA sequencing. This year's, we have a prize called the Russ Prize, which is given to someone who's done outstanding research in biomedical engineering. And NAE member David Walt won that prize for his microwell arrays. David was the founder of the technical founder of Illumina company on the West Coast in San Diego. It's been used, this technology has been used to sequence DNA of all of us. And the first genome was done at the cost of $1 trillion. Today, Illumina can do it for $200. Tells you something about the advances that can happen when you keep at it. Innovations by Irwin Jacobs and Anna Viterbi in Qualcomm led to new concepts like CDMA and allows us to make wireless communications rapid, reliable, and portable. And the personal computer, which came around early 1980s. I was lucky or unlucky enough to have one of the first ones that I had to reboot 6, 7 times a day. But who thought that, who thought it would catch on? I wasn't certain it would, but now we can't do without a PC. And now we're talking about mobility, electricity revolution, and making things run by electricity vehicles. So I'm very excited about what's happening today and tomorrow. Examples of creativity abound in engineering and touch society in tangible ways every day. Think if you got up in the morning, you go to work, think of every second you look at something and say, how did engineering touch my life? You're going to have a list of over 100 things by the end of the day. So I think about engineering as the expression of science on society, often before the science is known. And engineering and science work best when they work together. And that's what's going on here at University of Illinois. I saw some great examples of it this morning. The NAE's call to action video was developed as part of a $100 million fundraising campaign for the Academy, and it called Leadership in a World of Accelerating Change. The campaign aligns with NAE's 2021 to 26 strategic plan that places a focus on people, systems, and culture. Important things for us, people, systems, and culture. And our video is a sounding call to make engineering visible and public and attract young people from all segments of society. We must create an engineering field, as Bill Wolf said, that is more open and inclusive and diverse and brings in all elements of society. Together we can make a difference by focusing on people, culture, and systems. This is our call to action. So what a wonderful program for today and tomorrow. And I'm going to learn a lot. Mobility Electrification Revolution theme of this meeting is both timely and necessary. And as we transform our national transportation system to low-carbon electrical energy, we are faced with many challenges. But we are also presented with many opportunities. And I think that's the way you should look at talking to the young people here. Challenges equal opportunities. We will learn about some of these opportunities today and tomorrow, and perhaps learn about some answers to the challenges. I hope you will take this opportunity to learn from the exceptional speakers who will be presenting their work, and I encourage you to network with the experts who are on site at this meeting. I look forward to a stimulating set of talks and discussions. I look forward to learning a lot, And again, I thank the University of Illinois for hosting this very informative event. Thank you very much.
Thank you, Dr. Anderson, for being here, for your leadership to the nation, and we are honored to call you one of our alums. So thank you for being here. Next, I'd like to welcome Dr. Robert Jones, the Chancellor of our great campus. Dr. Jones.
Let me start by saying, first of all, good morning to each and every one of you, and to Dean Bashir. It is certainly my great privilege and an honor to be here with you today, and to be in my 7th year serving as the Chancellor of the University of Illinois, Urbana-Champaign, which we like to remind people is the state flagship research and land-grant university. And it is my singular pleasure to formally and enthusiastically welcome each and every one of you, the members of the National Academy of Engineering, to this regional meeting at our great university. I would be remiss if I didn't particularly thank the Granger College of Engineering for hosting this event today. And again, it's always good to see my colleague, President Killeen, the president of the University of Illinois system. So, Tim, thank you for your engagement and your walk down history lane to remind people of all of the key players that have helped shape engineering and innovation, have run squarely through this university. And so it's always good to be reminded of the role that this university and others similarly situated have played in shaping where we are today, the role of technology improving society for life. And I can tell you, in addition to the Nick Holianiaks and other folks that Tim mentioned, I find it rather ironic that one of the great innovators is also here during this time period. I had the great pleasure of hosting Martin Eberhard. And some of you may, hopefully all of you know who Martin Eberhard is. The founder of Tesla is here during this same time period. And I can tell you, it was really gratifying. The dean and myself and a small group had the chance to spend, it was a long dinner. Let's just say we got into some engaging conversation because Martin's wife, Carolyn, is also an engineer and a graduate of this university as well. I mention that just to emphasize that as Chancellor, I could not be more proud across the board, as John has indicated, and I was very pleased to learn that he's an alum as well. But as he indicated, across the board, engineers have helped shape our society in profound ways. And I could not be more proud the role that the University of Illinois and Urbana-Champaign has played in that whole ecosystem, and the fact that you are focusing your meeting today on a very critically important issue of mobility electrification and how it must revolutionize transportation. So I just think it's more than just ironic that all of these things are kind of flowing together. I realize that there are a host of other people that are going to be standing before you today, and one of the things I try to do as Chancellor is not to spend too much time at the podium pontificating, but I am just very deeply honored to be here with you today because I'm probably maybe the only person in the room, well, I don't know about Susan, maybe Susan and I, she's not exactly an engineer, but kind of an engineer of sorts. But I am trained as a plant physiologist, and so I'm probably kind of the outsider in the room today. But that does not diminish my enthusiasm for the reason that you are here. And these regional meetings are critically important to bring experts together so you can share ideas and you can think about the future. And as I said, I believe the future, particularly in this topic, runs squarely through universities like the University of Illinois, Urbana-Champaign, and so many others. And it is critically important to the future of our country and the world. And when you talk about transformative ideas and game-changing innovation for the 21st century, I think you'd be hard-pressed to think of many more visible and more imminent issues than the electrification and transportation system. So I certainly cannot think of a better group to be assembled to really take a deep dive and engage in conversations about what's the next level of innovation, where are we going with this, and what is the best path to get us there. So let me just say on behalf of the entire University of Illinois Urbana-Champaign campus, and for those of you visiting for the first time, we certainly welcome you for the first time, and we welcome back those of you who've been here in the past. And we certainly know and very, very proud that there are so many of you who at one point or another in your career have called this university home. So welcome back to Urbana-Champaign. And we're very, very proud of the work that we do here that's at the core of why you're gathered here. And we could not be more proud to host you here in this land-grant university, the flagship research university in the state of Illinois. Enjoy your time here, and thank you so much for allowing me to have a brief word or two on the program today. Thank you very much.
Thank you, Chancellor Jones. Next, I'd like to invite Dr. Susan Martinez. She's the Vice Chancellor for Research and Innovation for the whole campus and a great partner with us on many, many large projects. Susan.
Thanks, Rashid. It's great to look out and see all these faces. It's just wonderful, and I'm privileged to, along with President Killeen and President Anderson and Chancellor Jones, to welcome you today. It's really a delight to have you at this wonderful event. I probably don't need to tell this group this, and I'm sure you know that the federal government is really leaning very heavily on America's research and engineering institutions, and it's to solve some of the most pressing, complex challenges that confront society. We are seeing a once-in-a-generational funding opportunity like I haven't seen before, similar to the Manhattan Project, similar to the moonshot, similar to sequencing the human genome that you talked about, President Anderson. And it's to build really a better future for our nation and for the world. So I love the call to our younger people to really think about this, because this is where you're going to see impact throughout your career. Like the chancellor, my chancellor noted, I'm not an engineer, but over the 6 years that I've been the vice chancellor for research and innovation, I've spent a lot of time with the engineers, a lot of time with some of the people in this room, and I'm glad you called me a partner, Dean Bashir. I feel like, almost an honorary engineer. And when I was a student here, I spent a little time on Green Street, President Anderson, but I spent a lot of time north of Green Street on the engineering campus. So it's just a really wonderful community. So I feel like I can say with authority that no one is better equipped to build the future than the people around this room. It's just a fabulous community, very creative, very forward-thinking. Here at Illinois, we really pride ourselves on interdisciplinary work, the ability to cross disciplines to solve the most complex society challenges. I think internally, once people are here, they notice this. Our stakeholders notice this. Our partners notice this from the outside, and I think it's very special. So while gathering is focused on the electrification of our transportation systems, we know that scientific advances don't really happen in a vacuum. We harness those other disciplines. Improvements in battery power, or in cybersecurity, or in the nation's energy delivery infrastructure. This is all important. And just like the Manhattan Project and the moonshot and human genome sequencing that we've talked about before in other decades, the results, the innovations that will spill out of that will spill over into other parts of our society. So you're not only packing the Mobility Electrification Revolution, but so many other fields. There's a lot of work to do, so I'm just going to let you get to it and wish you a wonderful, very productive couple of days. Thank you very much.
Thank you, Susan, and thank you all for being here. So just a couple of quick comments, and then I'll introduce our first keynote speaker. So our college also has a very special connection, of course, with electric machinery, electric power. Our name is Granger College of Engineering with the Granger Company. So in 2019 was the 100th year anniversary of William Wallace Granger graduation from our college. So that's sort of the length of that relationship from the time that he graduated from the company and then stayed in touch with us. But that was also because of the great faculty that we have here that kept that connection and that relationship. And you'll hear more about that a little bit later. But I just want to make the point that there was a time, as you know, that many institutions across the country thought that power engineering, as it was called, is going to go away. and many of our pioneers in that area here kept on pushing forward, saying that no, this is really important to keep moving forward. And that connection with the Granger Foundation certainly helped us a lot doing that. So, and now it's back. Power and electrification is back in a very big way. So we have this very special connection. Our college is named after, and we're very, very thankful to the Granger Foundation, and I just wanted to acknowledge that. So with that, I'd like to now welcome our first keynote speaker of the event, also the organizer of the event, Phil Krein. He holds the Granger Emeritus Chair in Electric Machinery and Electromechanics. He's a professor of electrical and computer engineering. He was the founder and director of Solar Bridge Technologies as they developed AC photovoltaic panels. He received the IEEE William E. Knoll Power Electronics Award in 2003 and the IEEE Transportation Technologies Award in 2021, and he was elected to the National Academy of Engineering in 2016. Phil, would you please come and give your talk? Let's give him a round of applause.
All right, we're working two computers here simultaneously, so we'll see how we want to do the control. Are you going to bring it up from your end? Or do you want me to bring it up from my end? Okay, he has control. I don't know whether to fight with his mouse or not. Yep. Okay. I want to do more than just set the stage at this point, and the title in the program is sort of out of order. So I want to set the stage a little bit with some of the memorials we've been talking about, and then put a broader picture on to electric mobility and where we need to be headed, and maybe give you some things to think about that perhaps you haven't heard before. So start off really recognizing the three giants in their respective fields we heard about. I'm not adding Gordon Moore only because he doesn't, his linkage to Illinois is a little bit more nebulous. The others are much more direct. But in particular, Nick Holonyak, you remember the citation on his election to the National Academy specifically mentioned things more than just the LED. We continue to celebrate some of his activities in light-emitting diodes and other things, but he was certainly a leader on the team that invented the silicon-controlled rectifier, the semiconductor thyristor, that really kicked off a lot of the power revolution we'll see today, and we'll talk about that here in a moment. He earned his doctorate in 1954. It was John Bardine's first graduate student, so we have a nice connection historically back to the invention of the transistor. And I'm not going to read off the awards, but I wanted to be sure that you had this in your program. And then my very close colleague, Pete Sauer, passed away just after Christmas. The day before that, he'd been sending me emails about all the things we needed to be working on, so I know he was working right up until the last moment. A lot of his work related to the dynamics and operation control stability of power systems. He entered that field not too long after the major New York City blackout in the 1960s, when we began to realize that we really didn't know how this massive machine works. The electric power grid in North America is indeed the largest machine on the planet. And we have to make sure it runs properly because it is a very distributed piece of equipment. He also was the co-founder of the National Power Systems Engineering Research Center, which continues. a very active collaboration among about 15 different universities across the nation, and helped found the company called Power World that does a lot of commercial software for power system visualization. And then Bill Wolf, we heard a little bit about his background a few moments ago, but I want to, I will link him to some of the topics today here in a few moments. So let me do that. Like I said, I want to set the stage. So what's the connection, right? So here are Nick's connections, really, to what we're talking about today and tomorrow. The silicon-controlled rectifier, the SCR, which was commercialized in 1957 at General Electric, actually did literally drive the reinvigoration of the electric car. Within a few years of that device becoming a commercial product, there was a complete new set of projects in how do we build electrified vehicles. And this is just one example that one of my colleagues, who's now at the University of Houston, pointed out a few years ago. The electric Corvair, the Electrovair, this is version 2 from 1966. And I pulled this up because I was able to find a picture under the hood showing the motor and the SCR inverter set. So, you know, this device really was the only choice up until about the 1980s in terms of how you actually accomplish electric transportation. And then Pete's work, the most challenging thing in the power grid is that you have to balance the supply and demand continuously on a millisecond kind of a basis. Economists really struggle with that. They like to think of supply and demand as something you can balance over periods of years or months or maybe days. We don't have that much time. We have to do it actively and continuously. And this is an example of a dynamic signal from the Pennsylvania, New Jersey, Maryland, so-called PJM operating zone, which, by the way, includes Commonwealth Edison and Chicago. That's a story for a totally different day. But really zoomed into a few-minute window, one of the very interesting things is that electric transportation becomes an almost ideal flexible load to help offset that. And indeed, a lot of the research that we've been doing, including with Pete in the last few years, has been how do you integrate that? How do you take advantage of it? How do you make it a resource back into the power grid? Basically, the challenge with the power grid is that although supply and demand have to be well matched, it really doesn't work that way, right? When I walk in this room and turn the lights on, I'm not making a phone call or getting on a website and warning Ameren that I'm going to do that. I just turn the lights on. So there's not much on the load side, and trying to make that appear with the demand side is an emerging topic, and electric transportation plays a big role in that. And then Bill Wolf actually did a lot of early work in software reliability, and in particular on hardware-software co-design. And these are absolutely at the foundation of all the things we do in electric transportation. None of this would make sense. None of the things we do today would even be plausible if we couldn't talk in fairly rigorous ways about software reliability. And that's not just because vehicles are dominated by software, it's also because moving forward, and as we have more interaction, we have to be able to stake our lives on the performance of software systems, literally. Now, the other connection, of course, that's been going on recently is we are celebrating this year the 75th anniversary of the invention of the transistor. Dating really from Bardeen and Bratton doing their experiments in December 1947, where they finally got some really interesting results. And of course, all three, Bardeen, Bratton, and Shockley, were awarded the Nobel Prize in 1956. You hear a lot of different things about Shockley, especially in this campus, that I will not raise. But let's just say that all three of them were central to the revolution that has gone forward. Originally, of course, it was the tungsten contact point on a germanium crystal. And John Bardeen gave a very detailed paper about how that actually works, published a few years later in Science. And I encourage people to look at that. But what I want to get to today is that we really are working at two extremes. So we hear a lot about microprocessors and work at Qualcomm and work at Intel and others, and 4 nanometer scale semiconductors going on at TSMC in Taiwan and so on, right? 100 billion transistors on a single chip. Well, at the other extreme in the EV world, it's more like one device. So giving you a scale, that little block on the left there is a commercial product that's about 10 centimeters square, and it is basically 2 transistors. And its ratings are such that it can drive an electric vehicle. It actually needs 3 of them working together, 3 pairs. But whether it's 100 billion transistors on a chip or 1 transistor in a great big package, you know, we are at those 2 extremes, and the things we're going to see in the next couple of days relate to those extremes. In the transportation world, we're also moving to other materials, most notably silicon carbide. I'm sure some of the speakers will be talking about that in the next few sessions. That actually has dramatically changed the practicality of some of the new systems. And we have a long way to go, but we'll get there. Now, Martin will be here later in the afternoon. I don't think he's here right now because I know he's in the Illinois Leadership Program most of the day. But transistors did indeed change everything as we went past the SCR and moved into other things. A company called AC Propulsion in California actually was contracted and hired some people who had been working at AeroVironment and some other places. They built a very interesting powertrain that we learned about a long time ago for what was called the General Motors Sun Racer, which is a demonstration solar-powered car. And then they very unfortunately named General Motors Impact, which fortunately they renamed the EV1, but then eventually, as you know, they crushed them, and I don't want to bring that one up again. Anyway, the T0, the Impact, the EV1, the Sun Racer actually share more than a genome. They share a very small team of designers who really showed us how to use modern transistors to make transportation electrification happen. And there's Martin sitting behind the driver's seat of an AC Propulsion T0, which was actually pre-Tesla. So you get some idea of how this began to come together and really motivate things. And, you know, the GM EV1 was actually a very nice piece. I had the chance to drive one of them one time. That car had what was called the smile factor, meaning that anybody who drove it, when they got out of the car, they could not stop smiling. And of course, there's some other things like that today. And we learned very quickly in those projects that electric vehicles are something that people want if they are done properly. So with that, I'd like to spend a few minutes here talking about where we are headed toward electric transport and the revolution that's behind all this. And I want to start off by reminding ourselves, and the room is not completely engineers. I know there's some policy people and many others here. The end goal is not fancy, wonderful cars everybody likes. I mean, that's the wonderful commercial goal. The end goal really is mobility for everyone and everything. Solving people's mobility and transportation aspirations. People everywhere in the world aspire to personal freedom and flexibility. One of the first things you see in any emerging economy as people begin to bring themselves up is they buy automobiles. And looking back, we can say, well, maybe that isn't all that sensible, but that's the reality, and you have to look at why are people doing that. So what can electrification play in terms of enabling this kind of a role? How does electrification help enable unlimited mobility for people and for goods? How do we make it effective? How do we make it fully sustainable? I mean, we talk about decarbonization. It's more than that. It's the complete sustainability picture. And although we will be talking about different kinds of vehicles in the next couple of days, keep in mind, we're not just talking about vehicles, we're talking about anything that people need to resolve their personal mobility challenges. So it does all come around, and it's not always things on wheels that go on our roadways. And we'll hear a lot about off-road and many other applications as we go on. We do indeed expect that electrification will help enable universal mobility. And here are just some examples of the challenges, right? How can I build an intelligent transportation device or system that can enable a blind person to drive? How do I build a transportation system that can transport a child or a person who has very limited physical abilities to a physician, to a doctor's appointment? How do I get past the issues of dense urban environments and get past traffic and congestion and other things? I can't do that just by giving everybody lots more transportation options. It needs to be a lot more cohesive than that. Delivering fresh food around the world is certainly something that we're all aware of. How do we do that at best environmental cost? And yes, Tesla is rolling out semi-trucks to begin achieving these. I'm not quite sure that the first example should have been Cheetos, sort of a non-food, but nevertheless, Frito-Lay has actually a big footprint in Champaign County. Those of you who actually don't know it, I am told that almost all corn chips made by Frito-Lay east of the Mississippi River are made with corn from Champaign County. So we, in fact, have lots of coordinating roles here. One of the things, though, that I would like people to understand is that the costs and benefits sometimes are not taken very realistically. And certainly in my experience, people really seem to overestimate the costs of transitions. And it scares people, it holds them back, it really kind of inhibits moving forward. And I think they underestimate the benefits. So here are two wonderful pictures I found. One is a picture of Manhattan taken in May 1973, which many of us are old enough to remember when that would have been a typical day in New York City in the springtime. And here's a picture a few years later, April 2021, taken by some bloggers, which in fact is a typical day today. You know, that did not happen by accident. It happened because of the federal Clean Air and Clean Water Acts. I'm from Cleveland, Ohio, and I remember the last time the river burned, and that city has completely transformed. And again, I think people vastly overestimated the cost of cleaning up and making things better, and I think they vastly underestimated how beneficial it would be when we were finished with that. So let's talk about some electric vehicles and systems from a long view. It's kind of curious that really only in the last few years have electric vehicles caught up with what we could do in the past. A friend of mine owns that 1914 Detroit electric car that we see there. Detroit Electric was a joint venture of Henry Ford and Thomas Edison, okay? And that was considered kind of the premier car to have, the Tesla Model S of its day. You know, it was a top-end electric vehicle, and it still runs, and he actually managed to find some nickel-iron batteries to run it with. And today, finally, the Tesla Model S has kind of caught up with that level. Now, performance-wise, they're not the same, but in terms of how they really fit into the system, it's very interesting that it took essentially 100 years to come around and bring that to the point where it could have the similar kind of effect on society. So, why do we explore electric transportation? Why do we explore electric and hybrid vehicles? And again, setting the stage for the next couple of days. Energy reduction, they are more efficient. Energy flexibility. My plug-in hybrid car gets charged at night in Champaign-Urbana, which frankly means it runs on nuclear power. It's hard to do that any other way. Emissions reduction, including but not limited to carbon. And the obvious thing, and people ask about this all the time, if you do this wrong, they'll all be powered with coal. Yes, that's correct. We have to do it right, and we have to keep those things in mind. And there are opportunities for operation control, autonomy for the vehicles, and really related back to the power grid. And it's curious that in the long run, you actually find out these come with lower operating costs and higher performance. So, you know, there's a certain amount of win-win here. On the other hand, we can fall into a lot of fallacies very quickly. One of them was the one I just mentioned. Oh, if everybody had an electric car, we'd all be running them on coal and the pollution would be terrible. Yes, if we completely screw it up, that's probably accurate, but we can do better than that. Here's my favorite. An electric car, I hear this a lot, electric car will really need to match anything we can do with a conventional fueled vehicle. Well, first of all, it doesn't make a lot of sense because there's no baseline. Which fueled vehicle? Ford F-150, you know, a Yugo, for those of you remembering that, or a Morris Mini, or a sports car, or a sedan, or a hatchback, a minivan. I mean, what vehicle are we talking about? There's no baseline. In fact, there's so much differentiation that it's really hard to try and pin that kind of thing down. And the second thing is that we find that when people have electric or hybrid vehicles, they're changing their behavior. And it's not like they're sacrificing a lot of things. They just do things a little bit differently. They don't use them the same as fuel-driven cars. There's a real danger of building the future based on the past. And here's one of my favorite pictures. Martin Eberhard pointed out to me after I found it that actually is a horse stable that has been converted into an electric vehicle charge stable. And the idea is exactly that you take your car there at night and it gets watered and fed, so to speak. And then the next morning, of course, you're a rich person, you send your chauffeur to retrieve it and bring it back to you. You're treating the car just like a horse, okay? We know that doesn't work. It doesn't make sense. It's not the right way to do things. So repurposing a car to match a horse, repurposing an electric vehicle to match a fuel-driven vehicle, this is not the way to build the future. Things will be different. How different? Extreme performance we hear about, right? You see these ridiculous numbers, you know, 0 to 60 miles an hour in 2.5 seconds, which, by the way, is not a safe thing to do, right? You could do it on the track in Indianapolis, but for crying out loud, don't do it on a city street or a freeway. Motor response very quick. I can buy motors out of the Grainger catalog that can change their torque plus or minus 100%, about 100 times every second. You know, I don't have to spend lots of money for fancy equipment to make this work that well. I can move power around, and I'll give you some examples of that here in just a moment. And there are new kinds of performance capabilities that we just don't have with the things we're used to that I'll bring up some of. I just mentioned reconfigurability. So here is a very rough electrical diagram from an electric ship. And there are power transistors, switching power transistors, power electronics all over the place here that basically allow this whole system to be reconfigured dynamically all the time. Why would you do that? Well, different mission profiles, different use cases will basically emphasize energy flows and power needs in different parts of the system. You know, in a Navy application, there are obvious ones of trying to make things reliable and robust, but it applies to electric ferries, it applies to all kinds of large-scale transport and many other things. And we are actually applying those methods to a lot of other relatively large mobile systems. I think that John will probably talk about some things like this tomorrow, but here is a Deere loader that was deliberately designed to be hybrid electric, and they found at least 30% benefits, not just in the fuel and energy consumption, but also in the performance. they can actually move more material at a given time, substantially more than they can with other systems, because you can move power to the right places. You move power to the shovel when you need it. You move power to motion when you need it. You can reconfigure that system just almost instantaneously to do what you need to do in the best way at any given moment. New kinds of performance capabilities. I'm looking forward to the day when we can be a little bit more sophisticated about the mechanical engineering and build cars that can actively avoid collisions. We're getting there, right? We have automatic emergency braking, but it's not out of the question that a vehicle with a certain amount of autonomy can actually begin to pick its path. We do this now in some aircraft systems. We can, presumably, we can figure out how to do it in automotive applications. You could reconfigure crush zones. You can do all kinds of other things. Of course, I don't want to get anywhere near the collision in the first place. I want my autonomous driving thing to be a defensive, anticipatory driver that never gets into trouble. But nevertheless, there are new performance kinds of things we can do. Electric aircraft, very interesting topic. I think about 5 years ago, we used to talk about more electric aircraft. Here's a wonderful example, Boeing 787. But fully electric aircraft wasn't even a joke. It just wasn't even something that you could have any kind of conversation about. Today, we're actually seeing very quick movement from concepts to actual test platforms. There are something like 30 credible startups in the United States working on fully electric aircraft, mostly at small scale, but certainly in many ways that we never would have anticipated. And we'll hear about some of that during this event. The NASA X-57, X-plane always sounds like it must be something wonderful and fancy, but it just means the experimental test bed. And this little converted Cessna is something that is being explored quite aggressively for a variety of different electric propulsion concepts and other things, and making quite a bit of progress. And maybe someday we'll have something like that NX3 concept, the full-size turbo-electric jetliner. Well, I don't want to, for the electric vehicle folks, I don't want to leave behind the elephant in the room, which tends to be charging infrastructure. This is one of those things, though, where you can overthink yourself out of the problem really quick. And I keep reminding everybody that, we got to go back to basics and think hard about the objectives and what people actually need in terms of how that happens. Should we be emulating fuel-driven vehicles? And, I've already sort of predicated what that answer is, but where are we headed with that? There are issues of safety. There are perceptions about safety issues as well that kind of get in the way. Charge rates compared to connection times, we'll talk about that in a few moments. So the question is, do we already have the infrastructure in some sense? Can we just use conventional receptacles and outlets for our passenger vehicle needs? It would sure be nice and cheap. I'm not a fan of these big, fast, high-powered chargers that do a lot to try to emulate gas pumps, because I don't want the EV to emulate a fuel-driven car, and that's just not necessary. And indeed, now we start saying, okay, what's the data? The U.S. average daily car travel is 29 miles. That actually is not a useful number. And I had one of my students go through that, and I think she has a poster out at lunchtime. I think she'll be able to tell you why that number isn't really very helpful, right? Because if I drive 10 miles every day and then I decide to drive from here to Denver, okay, my average is what it is. That doesn't tell me much. The more meaningful number comes from federal survey data that actually shows that less than 5% of passenger car trips, daily trips in the United States exceed 31 miles. Okay, so 95% of the time, somebody can be kept happy if their car can go 31 miles. Now, that's a good thing, and I need to understand it. I can get carried away with that. It doesn't mean that I'm going to be able to sell a car with 31 miles of range, because 5% of the time it's not going to work. okay? But it does mean I need to figure out in an engineering sense what these numbers actually mean. And electric vehicle drivers seem to seek out simplicity, convenience, and other things. And you do get this division. It turns out that that number, even in places like Los Angeles, the number is relatively low in the big urban centers. People, and whatever they think, they're not driving as far as perhaps they might think. Whereas we get into the rural areas, and even there in rural Illinois, the color gets a little bit darker. You know, there are places in this area where people have to go 25 miles just to get to the grocery store, a decent one. And there are places in West Texas where it's more like 100 miles. You know, and if you're going back and forth to the grocery store, you got 50 miles right there. So, you know, we have to be careful not to generate an urban-rural divide as we carry along with some of these issues as well. So it does, there are a lot of things that kind of circle back and around. But how much do we have? How much do we need? How much infrastructure is really there? There was a report from the White House just a few months ago that said we have about 130,000 places nationally to charge electric vehicles. Well, that's ridiculous. The National Electric Code requires an outdoor outlet on every dwelling unit in the United States, okay? Which means that there are hundreds of millions of outlets sitting out there, maybe ready to be used. They certainly exist. And expanding that capability, putting a bunch of outlets on the wall out here by this conference center is not a complicated or highly controversial kind of a project. Now, that's not going to help for long distance driving, but it hits that 95% issue. If I can conveniently charge at home and work 95% of the time, that will be incredibly helpful and make life convenient and easy. There's a picture of a lamppost that I took in Lincoln, Nebraska. It turns out it had a locked cover on it that somebody broke off. I told them, why in the world don't you have a sign on there that says EV charging? Right? There it is. There's the charging station. I don't need to do lots and lots of work to try and make this happen. Now, in some places, people have already gotten clever about this. So, for example, here's a picture taken in Regina, Saskatchewan, where people use block heaters, electric block heaters, to keep their cars warm enough in the winter so they'll actually start. Well, I look at that and I see a whole forest of electric vehicle charge points. You know, it's not that hard. And some of my colleagues look at that and say, oh, you know, it's not safe. There's cords going through the snow and everything else. Well, people have been doing that in Canada for a very long time. You know, and yeah, we have ground fault interrupters and other things. I'm sorry. It's just, you know, using electricity is not a fundamentally dangerous activity. You know, we all understand what the hazards are, and they're real, and they're not zero. But I think we all routinely use electricity and don't think too much about it. And as it says there, there's an entrepreneurial group in Finland that has basically, in Finland, there are about 3 million cars and about 1 million block heater outlets already. So essentially, they said, gee, all we have to do is put signs up, maybe change some software a little bit, and suddenly we have 1 million electric vehicle charge points. We don't have to do anything. And my colleagues in Norway tell me that, yeah, well, you know, when I go up north to the ski resort, there's outlets on the outside wall at the ski resort, and you just plug in. You know, nobody asks you what you're doing. You just plug your car in, it's all good. Okay. Can 120-volt outlets really support electric vehicles? Tesla figured out that one way to think of this is to put charging into a speed. So charging out of a 120-volt outlet is only about 5 miles an hour. Oh, that takes a long time. Well, a passenger car is parked almost all the time. So if it's easy enough, it's not that big a deal, right? I got to be able to get to it at home or work, but, you know, yeah, I'm at work for more than 6 hours a day. I hope I'm sleeping for more than 6 hours a day. You know, there's time. And if I could get an outlet overseas in Norway or someplace, or even a tool out in the United States, I can get about double that, if that helps, if it matters. Or I can do this, right? Faster charging. This is what a lot of people are trying to sell us right now. Dedicated what's called level 2 charging. We have some around campus. The last time I looked at survey data, they used about 8 hours a month. If I can find a basic outlet in the garage with a sign by it, there will be somebody plugged in all the time. So interesting use case. This lady seems to be very happy to have found a charge point. I don't think she's done the math and realized that they're charging her about 4x for the energy versus what she would have been able to get at home. And she may not be so happy once she figures it out. There's no question that those chargers have to put a big premium on the energy cost in order to recover their maintenance costs, the other requirements. You will not be paying the retail rate for electricity anytime you plug in a car. Now, if you find a parking garage where they're giving that away to you, that's great. The chances are they're just rolling in as a parking charge. That's fine. But you get the idea. And it's too slow for long trips. 25 miles an hour is not going to help me if I want to drive from here to Minneapolis. And it doesn't benefit me that much for the 95% of the trips because, if I can plug in at work and just walk in and do my work and come back to my car, it'll be full. So, do we need them? Or are we being sold a bill of goods, right? Fast charging, we can't avoid, no question. It's vital for trucking. It's very important for long distance driving. But we would expect it will cover only a fairly modest fraction of the energy costs. Filling stations today, fuel-driven filling stations today, right, cover essentially 100% of transportation energy needs. Moving forward, if a filling station with fast chargers is covering 10 or 15 or 20% of energy needs, the business model's got to change. That's not going to be a simple expansion of what we do today. And we are seeing fast chargers going up in a few places. They're not really being used that much. The reason, of course, is the energy even more expensive from these. In fact, we're seeing that it basically has to match the energy cost of fuel in order to make the economics work. That's a problem. How do we really make this work? Location planning. I see lots of papers about location planning for chargers, but this chart is the one that I would say really tells me what's going on. This is truck volumes on significant highways in the United States. This one is 2017. The 2050 projection looks exactly the same, except that the numbers are higher. Okay, so everything's getting bigger, apparently. I don't know whether I believe that or not. But if you'll notice carefully, Chicago is the densest place on that entire chart. And in fact, there's a little triangle there, and I'm not going to get a pointer out. There's a triangle connecting Chicago, Indianapolis, and St. Louis. And there's kind of a little area there that's a little bit bolder than most. That happens to be Champaign-Urbana. So we sit right in the midst of that triangle of intensive freight flows in the United States. But here is a map of where we need fast charging stations for long distance travel and for trucking. And certainly some companies, and Tesla's one of them, are figuring out how to use this kind of a map to really begin to set up their networks. We don't need them everywhere. We need them in the places where people will use them. There are scenarios that one can take. These actually came from a question that I had, a discussion I had with someone in Tuscola, for those of you who are local. Some scenarios in a small town in this part of the country. Employees or residents might be parked several hours a day. Visitors might come in for 2 or 3 hours. And then you have the people who come in and want to have lunch and just park for an hour. Certainly those basic receptacles are ideal for the employees, the residents, the people who are parked for many, many hours. Maybe they work for the people parked a few hours. That's a little bit dicier. The level 2 is nice for that. The 1 hour visit probably needs the quicker kind of a thing. And then you start to say, okay, do I roll that into parking? Is it a paid parking lot? And this is included as part of the energy costs. You know, how do I really make this work? Or do I give the energy away in exchange for being a customer at the facility? There are many kinds of business models that can work on that, and I don't want to presuppose any of them. So quickly, I'd like to look at these problems in the future. So in some sense, we know where we need to be, let's say by 2040, right? It needs to be really easy to find places where we can plug in at home and at work, really any place where anybody's going to be parked for more than a few hours at a time. We need the fast charging infrastructure along well-defined pathways to support long-distance travel. And we need the communications, the billing, the coordination. We need to figure out how to make this work. And then we need to work backwards to 2023 and figure out how to build the path to get there. And I'm not sure it's that hard, right? Here's a picture on Wright Street, pretty much outside the ECE building, with a light post and a little box next to it that says electric. Okay, I need a post there with an outlet on it that says electric vehicle charger. Okay, it's not that hard. We can figure this out. One final thing, I'm trying to link this back to Pete Sauer and dynamics in the power grid. A connected car is a flexible car. If a car is plugged in, I can do things with it. And that doesn't necessarily mean the energy goes both ways. This example, actually, the energy only goes one way into the batteries. So there's two flexibility scenarios that are compared here. The Boulder dashed line is one where basically the owner has said, I want my car full by tomorrow at 7 a.m. And car, go to the web, figure out what the hour-by-hour electricity prices will be tonight, and given limits on the charge rates and so forth on my outlet, just figure out a schedule to minimize my energy cost. So when I come out, the car's full and I've paid as little as possible. That's actually fairly straightforward. The other one, which is more complicated, said, okay, instead, I told the utility, I want my car to be full by 7 o'clock. I need this much energy. You figure it out. Do whatever you like. And indeed, in this case, they've actually run the car against that dynamic signal we saw many slides ago, the very fast dynamic regulation signal in the grid. They're using the car's charger to kind of offset that. Now, I don't want you to look closely, but the chart never goes below 0. Okay, the car is always a positive charge. I'm not ever pulling energy back out of the batteries. Lots of people get worked up about that. Don't have to do it. And of course, the second scenario will be cheaper because now the utility is going to have to pay me because I'm providing a regulation service. So, you know, absolutely. Sounds like a great thing, right? We will head maybe towards self-driving transport. It's going to take a lot longer, I think, than most people understand. We had some people on campus about 6 years ago who said it would be next year, it'd be 2018, it'd be 2019. Yeah, okay. Autonomous driving is like anything else. It is the wave of the future, always has been, always will be. We will get there in different scenarios. We certainly are there in some specific applications. You know, self-driving transport is not unusual in airports. And there's a little still from an automatic emergency braking test that Car and Driver magazine did on a few cars a few years ago. So, you know, things are coming out, and I think augmented safety systems make more sense for the moment than autonomy, certainly for these kinds of vehicles. So some quick endpoints. I would claim that 95% of daily passenger ships can be supported from really basic electrical infrastructure that's, first of all, a lot of it's available. Second of all, very easy to expand. Trucking is different, but we have some location strategies that we can begin to build on. And vastly expanding this, I think, can get us past infrastructure questions and get us to the point where the state's ambitions to have 1 million electric vehicles by 2030 really can make sense. Now, some very quick things. Close up here. Today and tomorrow, we're going to hear a lot more elaboration on many of the underlying challenges here, more fundamentals and more future orientation. Please take advantage of the posters that will be out today during the break times, including during the lunch and during the afternoon break. We have the students ready to go. I want to thank the team that we call MARTEC, the Mid-America Revolutionary Transportation Energy Consortium, that certainly has inspired us. And then our colleagues at places like Ohio State, Wisconsin, Michigan, and Purdue, many of whom are here today, which is we really welcome you, happy to see you. And of course, our sponsors have already been thanked, so I can only keep repeating how grateful we are for that help. So with that, thanks. I think we have a couple minutes for some questions, and then we'll let you go into the next room for lunch. Yes? And by the way, we are trying to do a bit of a live stream here, so we'll grab the microphone and make sure that you can ask your questions in a way that can be heard.
What is the extra energy we need to electrify transportation come from?
Yeah, so a great question about if we were able to move everything in our transportation system to electric. You know, right now, very roughly, a third of energy, primary energy in the U.S. goes to transportation, roughly another third to electricity generation. Yes, that means we have to double our electric grid size. Two things that are interesting. Right now, the growth in solar and wind is actually on pace to get to that doubling much more quickly than we will get to that transition with electric vehicles. So some of that is happening. Second thing, I want to make you a little bit optimistic. We found the charts between 1929 and 1979, the electricity grid in the United States grew by a factor of 12. Okay? 50 years, factor of 12. We need a factor 2. We can handle it. We've been there. We've done that. We know how to do this. But actually, like I say, the growth path that we're on will get us there with solar and wind, frankly. So we'll see that. It's not going to be growth in coal and natural gas. So I can be really optimistic about that. Maybe one or two more, and then we'll hit lunch. Yes?
What's the real barrier in converting the receptacles to the wall chargers?
What's the barrier in converting receptacles into EV infrastructure?
Do that sooner. Yeah.
I think there are some of those barriers are policy. Interesting thing, for example, if we wanted to make 120-volt EV charging infrastructure readily available throughout Champaign-Urbana, okay, that is a community project. You need to have posts or other things throughout neighborhoods. You need to put electric outlets and parking meters and so forth, right? I mean, we can imagine how to do that, but it is a significant community partnership. The cynical answer is that the people who will make the money will be the local electricians and some of the other, really local workers, and the big suppliers won't make the money, right? The equipment's already there. It's not that hard. And actually, that is a bit of the problem right now. The other one, which is a little bit more subtle, the question is always who pays. And again, there are many different business models. Is there a web-enabled switch behind that outlet and you have an app in your phone? If it's at a restaurant, is there something at the point of sale terminal that says, okay, I need to turn on the outlet at space number 9 today because I have a customer with a car parked there? There's lots and lots of possibilities there. Do I pay an annual parking permit and that allows me to use outlets in this neighborhood without any other complications? Whatever, right? Certainly the California ISO people are saying, we're already turning down the solar in the middle of the day. Do we just make EV charging out of regular outlets free between 10 a.m. and 2 p.m.? Maybe it's as trivial as that. Or maybe it's 2 cents a kilowatt hour, whatever. So yes, lots of business ideas and policy things and community projects. I think the things we'll demonstrate that will be community-based projects. Yes. One more, and then we'll head off.
Thank you for the nice presentation. I was just curious, what are your thoughts on the ongoing efforts for grid management? You mentioned solar and wind, so I anticipate we'll have different energy resources and the distribution associated with that. So how are these being managed, large scale of power, distribution, and so forth?
Right, right. So she's asking the massive question of how we adapt to the grid to dynamically changing and variable resources and other things. And two answers on that. I mean, that is central to a lot of the research that we're doing in many parts of this university right now, and some of my colleagues at other universities are well aware of this too. An example, again, electric transportation, especially passenger cars, tend to be flexible loads. We can change the timing around. You know, the wind isn't blowing this hour, maybe we can charge a different hour. Weather forecasting needs to have a significant role in that. There's a lot more we can do to make that system interactive. The second, which of course is what we talk about a lot, is how do I most effectively integrate energy storage? Not just batteries, but many kinds of energy storage, and integrate in a distributed control that can bring that together with the grid most effectively to get the best operation. I mean, I'm optimistic because this is the kind of challenge we've been working on for a very long time. But certainly there are new things, and the notion that we have very, very dispersed control of the power grid is different than what we do it now. So we can anticipate some really interesting engineering challenges. I'm not worried that things will go belly up. I think transportation is, in spite of the rate of growth, the actual rate in terms of energy is quite manageable. And the flexibility, I think, is a really big advantage. All right. Thanks so much for everybody for being here this morning. And Kanan, lunch is right next door, isn't it? Okay, we'll see you in lunch. Thank you.
ready to start. Good afternoon, everyone. And so we are going to start with our first afternoon session, and the first speaker is Professor Imad Al-Qadi, the Granger Distinguished Chair in Engineering, and he's a professor in the Department of Civil and Environmental Engineering and the director of the Illinois Center for Transportation, ICT. So prior to coming to Illinois, Imad was a professor at Virginia Tech. He is a registered professional engineer and a distinguished member of the American Society of Civil Engineers. And Imad, please come up. So he's going to talk to us about the future of mobility and electrification. Thank you.
Thank you, Anna, and good afternoon, everyone. It's always my pleasure to talk to you about this topic, so I'll just go ahead and dive in directly. We are talking a lot about sustainability. Anything that we are working on these days, we have to talk about the climate change because it's impacting our public health, rising the sea levels, and of course, it's impacting the food security. And if we look a little closer to this, we'll find that this is impacted by two sectors more than anything else. The first sector, of course, is the transportation, which is the most impactful sector on the climate change. It's around like 27 to 29%, depends on the year we look at it. And the second is the energy. Energy, until 3 years ago, used to be the most impactful on the sustainability and the climate change. Therefore, we need to develop an infrastructure that it will accommodate these two impactful reasons on the emission for the mobility. So having a quick look at what's happened in the mobility market, we'll find just a year ago, the market in the connected and autonomous vehicle is around 76 billion. On the cellular vehicle to everything is around 630 million, and renewable energy around 860 billion, and electric trucks around 3992 million. Now, if we are moving, we'll find here that by the end of this decade, these numbers gonna be explode. So the autonomous and connected vehicle, that's gonna be at 2,900%, and the rest, you can read the numbers here. They are astronomical. So what's happening in transportation is moving at a very, very fast speed. Now, if we look at the current state of the EV infrastructure, the plan here is that the sales by 2030 is gonna be around 50%. And it is expected that they're gonna be 53, currently, of course, there is 53,000 charging stations in the US, 6,000 of those are fast charging. The national electric support coming from the federal government in the last year bill was $5 billion that is gonna go to the states for improving their electrification maps. And they have also another $2.5 billion that they are more flexible that any of the state can grab some of this money. And the state of Illinois and all the states, they have to prepare a program that's supposed to be completed by the summer of this year. And the state of Illinois has already done its planning. And I think maybe Rayeshi will be talking about this in a little bit. So to build a national network by 2030 that is going to have 500,000 EV charges is something that is currently on the map. But most importantly, we wanted to make sure that we have a designated EV for freight, and you're going to see here in a minute why this is very important. Actually, Phil this morning, he touched on this by saying that 95% of the vehicles, they don't drive per day more than 31 miles, which means that they can charge it at home if they wanted to. So the most impactful thing going to be here is the charges of the freight or the trucks. But looking here at the national goals for the EV infrastructure, we need to look at what is the electricity grid now in the United States and where it's coming from. So we find that 40% of that is coming from natural gas, and 22% is coming from renewable, and 20% is coal, and 18% is nuclear. So here the idea is to try to have a complete decarbonization by 2035. And that's going to require some advancements, such as the rapid deployment, and it is expected, or it's planned to have 30 gigawatt by 2025, and that's going to ramp up to 60 gigawatt by 2030. The same for the offshore wind to be around 30 gigawatt by 2030, and for the geothermal by 2050 to be around 60 gigawatt. Now, if you look at the electricity system in the United States and look at the states' distribution of where they are getting their electricity and power from, we'll find that there is very big difference between different states. While we are working on the electrification of the trucks, we were trying to see how this is going to be impacting the charges of the trucks from different states. So I'm going to be showing you here some of the extremes when we compare them to the state of Illinois. State of Illinois, luckily, we have like 52 of the energy is coming from nuclear, which makes it completely clean compared to other sources, and only 13% is coming from renewable. If we flip and we go to Washington, for example, we will find that in Washington, almost 76 or 78% of that is coming as a renewable energy because of the hydroelectricity that they have in the state of Washington. On the flip, we'll find that West Virginia is having almost 89% of that is coming from the coal, and you get to other states like Delaware, where they are using significant percent of their power is coming from the natural gases. So all this now, when you think about it, the freight is not usually local per state. It's usually across the state. Most of the freight that we are using in the United States, it's crossing the states, either north, south, or east-west. But also, this is impacted by the infrastructure. According to the American Society of Civil Engineers, who published every 4 years a report cards indicating what is the infrastructure status. And as you see here from these figures here, you can see, for example, that the roadway in the United States, it's given a grade of D. And the inland waterways is giving D+, but if you look at the ports, it's B-. But also it's important here that the energy is giving a C- as part of the infrastructure. And that was giving this C- was giving for several reasons. One is that it's outdated transmission lines that they have, the interconnections queues, as well as the use of the land for solar as well as wind. So we have few challenges that we need to address. One is whenever we're going to be using electrification or electrified mobility, we need to be concerned about the range anxiety. I mean, when this battery going to be need charges. The charging time, this is not maybe a big deal for vehicles, but it's going to be a major big deal for the trucks. The trucks, they don't have time for an hour and a half to charge their trucks whenever they are traveling. Also, the limited infrastructure that we have. Although according to the FHWA requirements, we need to have charges every 50 miles now, and that's what all the states they are planning to do and submit their plans. Excuse me. There is some work in developing a megawatt scale for charging system in order to address the instantaneous high demand that we have for the grid integration as well as the inadequate grid distribution system. So as we are moving into this, there is something which is important, which is the missing of protocols and policies, such as how we're going to be installing and operating all these EV chargers and systems, and how these going to be maintained as we go into the future. What is the percent of decarbonization that we are getting from this? And most importantly here, whenever we're talking about mobility, we're talking about multimodal transportation, which means that we're talking about air, sea, as well as land. And talking about this, I'm going to be just giving one slide about each one of these things. Here are some of the challenges that we have for the ports, which is moving into electrification. And as I said, that according to the ASC, they were given a grade of B-, but for the inland sea use or ports, that was giving a D+. So there is some work that it needs to be done. And some of the issues that we are dealing with is inadequate grid capacity for the ports, the insufficient infrastructure to meet the future power needs, uncertainty of the new equipment and the technologies and their associated cost, and the grid management and the optimization for the distribution of the energy resources, as well as the storage of the energy. Then we talked about the eVTOL, and I think the speaker next to me is going to be talking about this in more detail. But from the transportation point of view, this is a new area, and we are very much interested in it because UPS, for example, next year, they're going to be having around 150 of the eVTOL, and these ones, they're going to be having a range of 250 miles, and they're going to be able, I guess, to keep moving at the speed of 170 miles per hour. And these things here, some of the work that has been done at the University of Illinois, and it was supported actually partly by ICT, is to try to optimize this, which means here how we can make this here go longer by reducing the charges that it needs, or the time that it's going to require to charge, or the range for one charge. Now, as we are going into the highway, I'm going to be talking a little more about this for two reasons. One, it's my area of expertise, and second is because this is where the freight is. So if you look at the freight in the United States, 72% of it is moved on roads, and that's almost $17 trillion. So we're talking about most of the freight is on road. And now with the e-commerce, that's become more important as we are moving on. So we have 22.8 million medium and heavy-duty trucks in the United States that they annually travel more than 430 billion miles, and that consumes more than 55 billion gallons of fuel, which is really significant. Now, these vehicles, around 5% of all the vehicles that they drive on our roadways, but these are responsible for 24% of all the emission that we are seeing or that goes into, into the atmosphere. So one of the things that thinking about is why not having truck electrification? And that will be definitely accelerate the decarbonization. This is considered to be resulting in considerable saving, around 29 to 44%. And also that's supposed to be reducing the global warming potential for almost 89%. So this is really a good thing to do, but we need to also consider what are the challenges that we're going to be having for this. So one of my colleagues also worked on how this freight will be used in the future. As we are moving forward, you will have all these lines of trucks bringing the goods into distribution centers. From the distribution centers, these will be going by drones in order to get the packages to the different places. Now, what is the best way to use the energy in this case here? Are we getting all these packages by one drone, and each drone take the package and drop it into the address? And that's going to be definitely resulting in some congestions in the air, similar to the congestions that we have on land right now. Or that will be an optimized, and thanks for the work of Oyang. So as the vehicles is moving now, the drone's going to be start putting the packages, and while the vehicle is moving, and the drones come back to a different one. Even during this kind of activities, as the drone is going back to bases, that can be also another place for charging. So as we are talking about electrified mobility here, I think there is three things that we need to pay attention to. First is the technology, from energy harvesting to dynamic charging and to secure AV cave systems. Second is the infrastructure, how this is going to be impacting our infrastructure. And third, which I think is very, very important, we always lacking, is the development of policy and protocols. And because we have different, usually policies between the different states, and whenever we have the mobility is not constrained by one state. So as a truck, for example, is moving from Wisconsin or Indiana to Illinois, these trucks, they will not be changing their loads or the way that they are equipped when they enter the state of Illinois, because they have different policy or different protocols. Therefore, these things should be, in a way, discussed between different states and come up with, in my opinion, universal protocols. Now, let me talk first here about some of the technologies. Energy harvesting is an important thing in the infrastructure. At the micro level, this can be used as solar roads. This has not been a very successful experience so far, and the reason because they are ignoring an important part, which is the traction between the tire and the surface of the road, as this is an important part for, I guess, from a safety point of view. The other is to use it at the right-of-way, and even at the right-of-way, in some cases, that can be used as a noise barrier. And, of course, the solar canopy. Then we have, at the meso level, to use the wind, and that can be used on light poles, for example, in order to generate the energy that is needed for that particular infrastructure. At the micro level, there is the use of the piezoelectric as well as the electromagnetics in order to recycle the energy that it is coming from the trucks into the road and get it back in. And I'm going to explain this here in a little bit here. So one of the things, as I said, is trucks, they are not interested in stopping at the charging station for an hour and a half at this point in order to charge the trucks, because it's all about, I guess, the logistics and the economy of the trucks and how much they can moving. So one of the things is to have the dynamic charging, which will alleviate the range anxiety, as I mentioned, because a vehicle can stop every maybe 200 miles, but the truck cannot stop in less than 500 miles. I mean, that's what it is for the trucking industry. That's how they make their money. To eliminate the inconvenience due to charging time and reduce the freight costs. So one of the things that is currently being looked at research is to have contactless charging. According to our own analysis, it's going to be really costly at this time with the current technologies that we have, that we need to have the vehicle driving over a wireless charging for a mile in order to charge for a mile and a half, and that's absolutely not economic and not reasonable. So there is some more work that it's needed in that field from the electrical engineers. The other one is to have the contact charges, and that could be from the top or could be from the bottom, and that's something that has been used in Europe. Regardless, there will be some significant auxiliary roadside infrastructure that is needed in order to make sure that we have the power to keep these vehicles going. Here's a few things that we are researching in our group here right now is the dynamic vehicular loading. As you are driving, you always have some bounce in the car. Some of it you feel it, some you don't, because some have very nice suspensions and seats and so on. But there is always, when you are driving, there is some bouncing that's happening in the vehicle. This bouncing here is something that we will be able, this is here showing typical roughness of the road, and as you are moving now, you will find here that there is some, I'm going to show the next one. You can see here the vehicle, how it's moving. And this is now a source that you're going to be able to collect energy as the vehicles are driving. And this is part of some of the simulation that we're doing based on the load that it's applied to the pavement. Now, another thing which is really important is as we are moving into the electrified trucks, one thing which a lot of people maybe is not aware of, most of the damage to the roads is not coming from the wheels in the back of the trucks, it's coming from the steering axle, because the steering axle, you have one wheel, and usually it's carrying 14 kib, so per wheel, that's where most of the load is happening, while the other wheels, they do have, excuse me, the other wheels, they have like, let's say 18 kib, but they have two wheels on each side. So in a way, I just wanted to say that the steering axle is the most damaging in the pavement. And if you look at currently, where we place the battery is placed next to the steering axle, because that's where the gas tank is. So they take the gas tank, they put this in. Some people who are following the bills, last year, I guess, they introduced a bill at the Congress, which was accepted, is to increase the weight for the electrical trucks by 2,000 kib. The matter of the truth is the increase is going to be 9 kibs, and that's going to be very, very significant. So these 9 kibs, one of the things that we are doing right now is to see what is the most optimized way to place this? Is it going to be where the gas tank is or distributed among other axles in order to reduce the damage? But again, if you have a 9 kib increase and the total truck, loaded truck, just to let you know, it's 80 kib. So if you're going to be adding another 9 and you have a weight limit across the United States, this means that you're going to be having less goods to, I guess, to move, or you're going to be maybe stopping more in order to get the charges. So these are some concerns that it's really concerns. That's why the trucking industry, they are kind of like hesitant about what to do about this. Then there is another concern, which is the torque. So as you can, I guess some of you who drove a Tesla, they always love the idea that when they drive on the Tesla, it will take off immediately, boom. But this is a major problem for us when you have a truck. So the truck usually takes like maybe 60 seconds in order to get to the right speed. Now, if you're going to get it at 20 seconds to get to the same speed, that's going to apply a lot of shear on the road. Now, this shear going to look like this. That's based on our simulations. So you're going to be seeing something like this happening on the road as you are moving, accelerating, or braking with the truck. Of course, you are not seeing it in a vehicle because the weight of the vehicle is very, very simple and it doesn't do any damage per se. So what does that mean? This means here that it's either we're going to be doing a redesign for the new roads, or we're going to be spending a lot of money on the rehabilitation, and that's going to be indirectly also impacting the life cycle assessment or the sustainability. Then there is another thing here as we're moving, of course, into the electrical trucking platooning. Platooning is when the vehicles, they are driving behind each other. And many of you, when you are driving on interstate highway, you see the trucks, they love to drive behind each other because they know that they're going to be saving energy because of the wind, and there is 3 types of forces, and they know that they're going to be saving energy just by driving behind each other. Usually, depends on the state, the distance between them is like 200 to 250 feet. Now, people are proposing they can be as close to each other as 10 feet. Of course, that's not true, and I don't think it's going to happen in my life, but I think it's going to be something like maybe 50, 65 feet. That's where I think that's going to be in the platoon. So these trucks now, they're going to be driving on top, behind each other. And interestingly, just to give you an idea, for the state of Illinois, when we did our study, we found that during the peak hour, there is 87% of our interstate system is platoonable. If it's off-peak hour, that number increased to 93, which means that regardless, you're going to find that the drivers, they're going to be doing the platooning. And if they are driving behind each other in the same location, they're going to be more damage to the pavement. So what we're doing right now, this is here showing you a picture of what's happening. What we are doing right now is trying to have a control of the trucks, how they're going to be moving, and try to get them into sides so they will distribute the load without cutting the platoons, but different platoons drive at different locations. So the people who are saying that as we're moving into the autonomous and connected vehicle, we should be now reducing the lane width, I would say that absolutely will not work, and it should not. Okay, oh boy, all right. So let me go very quick here. I think we need to do some. You're gonna give me another 3 minutes. So let me move here quickly to this. I'll move on this. And I will tell you about what we are trying to do here, okay? So what as you can see from whatever I said earlier here, that this is a very complex problem. This complex problem, it needs to have different integration of the different talents and different brains in order to make this happen. So what we are doing here in Illinois, we're putting this Illinois Autonomous and Connected Track, which is going to be 2.9 track. I'm going to go with this 2-minute video here. This is going to be in Rantoul, which is the former Chanute Air Force Base, and there will be a control center, and this will be a 2.9 miles on 3 lanes, and the vehicles, they're going to be driving at 75 miles an hour, which does not exist anywhere, and it will allow us to do all different testing and validation and development for all the areas that it's related to transportation, including the energy harvesting, including testing under all weather, as well as we will be having 76 snowmakers that will allow us also to create the weather we want. You will be having the communications between the vehicles, as well as agricultural testing and transit, and the vehicles communicating, because what we're going to be seeing in the future, that the vehicles going to be talking to each other rather than stopping at the traffic lights, as well as we have testing, as I said, under all weather conditions that we're going to be creating, as well as testing of, or the response in the pavements itself. So, of course, different materials will be tested, different lighting will be tested as we move on. So let me move here very quick. This is going to be a state of the art. It's going to be also thinking about having this as a zero net emission. And it's going to be definitely bringing the research here. And it has very significant impact in the economy. We did this for the state of Illinois, as well as the return for the country too. And we believe that this is going to be a flagship for an entrepreneur work between the industry, the academia, as well as the public. We have already done with a few things, including the design of the 5G, the electrification, and the energy harvesting. And we had the company called AECOM finish the conceptual design, and we have also completed the business plan for it. So let me finish with this is my final slide, just to give a glimpse at the net zero future mobility. There is a demand that we have, and we're expecting that in 2050, there will be 700 million vehicles, and there will be 300, that's globally, there will be 300 e-volt or 1,000 e-volts, and there will be hopefully zero-emission ships at that time. There is 49% of the global electricity should be coming by that time from renewable energy, and the infrastructure must be ready for all these changes. And that's going to be through the climate change, digitization, smart maintenance, and the network-wide cybersecurity. This is going to require some integrated collaboration, and that's where we presented the IACT as a testing arena to catalyze the cross-cutting research between and development between all these areas. The implication, I cannot emphasize the need for policy and protocol developments. I think this is something we're going to be facing again and again as we're moving. So this is going to be, the policies that we have, it's going to be the safeguard for the net zero emission goal that we are putting forward. We need to develop standards and specification that, and protocols, of course, that it's mutually address the needs of the transportation, while at the same time, it's taking the resources or the sources of the energy that we have. Ultimately, I wanted to emphasize that even during COVID-19, the percent of fatality in the United States over the past now it's 3 years, has increased by 18%, and Illinois was not an exception. So frankly, this is what's going to help us to have a safe and robust system and dealing with data electrification. And Anna is closing on me. And thank you so much. I wanted to thank everybody here.
So Imad will be around, and so you can, I'm sure, grab him at the break if you have any questions. So we welcome now our second speaker of the afternoon, which is Kiruba Heron, the Granger Director Chair in Electric Machinery and Electromechanics in ECE. And he's also the director of the NSF Poets Engineering Research Center. And he's going to talk about net zero emissions in air travel and electrification. So let us welcome.
Thank you, Anna. All right. So I think Imad really set me up nicely. He talked about electrification of all modes of transportation. I'll talk about electrification of aviation and maybe highlight a few activities that we have ongoing here at Illinois. Now, we know many of you came from different parts of the country, and some of you probably flew here. I'm not going to flight shame anyone, but you probably heard numbers like if you flew here from LA, a return trip, accounts for about 900 kilograms of carbon, a single trip, right? Which is about a quarter of an average human's carbon emissions for the year, right? So that's the kind of impact flying has. So that's obviously, I'm trying to figure out how to go to the next slide. So that kind of sets the stage for the grand challenge in aviation, how to get rid of the emissions from air travel. If you continue with business as usual, this is an industry projection of how much carbon we are going to put into the atmosphere. Between now and 2050, that's going to be 21.2 gigatons of carbon over the next, roughly 30 years or so. Obviously, not acceptable. And we're not going to solve this by going back to what we did in the pandemic, going back to living in our basements and working from there. We want to fly around, we want to travel, but still decarbonize. And what has the industry done? They come together and said by 2050, we're actually going to go to zero emissions from aviation. And this, by the way, was updated from the target the industry had till just 3 years ago, which was to cut emissions by 50% by 2050. So if anything, we want to accelerate decarbonization. So the question is, how do we get there? Before we talk about the future, we have to acknowledge where we come from. Some of you here may be mechanical engineers, right, that have worked on the jet engine. So the last few decades of aviation has really been defined by the jet engine. This is one of the most awesome machines developed by humans. There's a fighter jet up there. There's a jet engine for a civil aircraft. Regardless of which one you're looking at, over the decades, we've improved performance from the jet engine. Every metric you pick, whether it's flight safety, thrust to weight, fuel efficiency, engine noise, all of these have improved dramatically. But one thing that you may already start observing is, yes, they are continuing to improve, and there are engineers working on this today, but you can start to see some level of saturation, right? So if you're going to look at transformational change, it may not come from us continuing to make the jet engine better. So look at alternate ways of propulsion. And electric becomes one tool to look at. Electric could be battery electric or hydrogen electric or other types of electric, which I'll talk about in a second. And this is, by the way, not new. I think I heard today that 1973 was something happened. Several things happened. Was it the transistor? I forget what it was. I heard that year, but it's also the same year that the first manned electric aircraft was flown. So this has been with us. That had a nickel-cadmium battery. It had an electric motor. People were able to fly this, stayed up in the air for several minutes and came down. And you can already buy a commercial electric aircraft today, fully certified by Pipistrel. That's the second aircraft up on top. And the teams out there that are continuing to improve this, longer range, more efficient, higher payload, all of that is happening. And this is, like I said, with hydrogen fuel cells or battery electric or hybrids, all of that's happening. And there's certainly eVTOLs. And sorry, Imad, I'm not going to talk about eVTOLs today. I'm going to focus on carbon impact. And if you worry about carbon impact, you have to look at the statistics. This data on the right here is a little dated, but still tells the story of today. Certainly in the US, almost 90% of the carbon emission from aviation is from the larger transport class aircraft, the single aisle and larger. Imagine a Boeing 737 type aircraft and larger, accounts for 90%. So you could make all the general aviation and small aircraft electric, and you're only playing with 10%. So we have to electrify the big guys. And that also is not new. And I think Phil mentioned this in the morning today. There's been a general trend towards the more electric aircraft, in the large transport class aircrafts, where we take some power out of the engine, convert it to electric power, and then power the auxiliary systems. So everything from actuators, environmental conditioning systems, anything in the aircraft other than the propulsion itself has been becoming more and more electric over the last few decades. The more electric is probably the Boeing 787, the Dreamliner. But look at the numbers. The auxiliary systems are about a megawatt of power being extracted from the engine. The propulsion power is about 40 megawatts. So we're still talking about only like 2-3% of the power in an aircraft is being converted to electric and becoming more and more electric. So the question is, can we electrify propulsion for this big aircraft? And the National Academies, who's here today, published this report in 2016 talking about the potential for decarbonization with using electric or hybrid electric as one of the tools. And there have been several other studies that show the promise of a decarbonization with electric propulsion. But what are the barriers? Why can't we do this today? Two basic questions. You need power and you need energy. So let's start with energy. This is a graph of gravimetric energy density, megajoules per kilogram, and volumetric density, megajoules per liter. And you see, if I can make this work, jet fuel up there on top. If you go with either hydrogen or batteries, down here at the bottom. Right? Goodness is way up here. So there's a huge challenge in going with battery electric. But I think the NAE president mentioned this in the morning. Engineers love challenges. A challenge is an opportunity. So we're not going to shy away from this. What we're going to do is be creative. How can you electrify one of those large aircraft, even when you're challenged with an energy source? Today, conventional aircraft fuel, go through a compressor, turbine, drive a fan. That's where we are today. Far in the future, those big aircraft could be powered with hydrogen fuel cells, electric motor, drive a fan. But in the interim, there are all these other options, hybrid electric. So you may be familiar with the series hybrid, parallel hybrid that you had in EVs or electrified automotives before we got to truly electric cars. And in fact, in addition to those traditional configurations, we have the turbo electric. If you're familiar with locomotives, so you have a carbon-based fuel. By carbon, it could be net zero. So we talk about SAFs, sustainable aviation fuel. So all of these options could be net zero, but we can improve upon them by generating electric power from the fuel and then running a whole bunch of electric motors that drive turbofans and have the propulsion. And some of these may not need any energy storage at all to get going. And as energy storage improves, we can certainly integrate them back in. What's really exciting is, so we start with electrification as one of the tools to decarbonize, but once you start integrating electric powertrains into an aircraft, now your design space is opened up. Electric power is easy to distribute and control, and this disruption is making engineers out there become a lot more creative. Most airplanes were used to tube and wing, and propulsion units either under the wing or at the tail. Now, with the ability to distribute the power, put a whole bunch of propulsion units around the aircraft, you can have concepts like a blended wing, distributed propulsion, eVTOL type aircraft. All of this become really exciting space for us to work on with electrification. Now, going back to the larger aircraft, so the National Academies has gone through all the reports out there and come up with targets. What are the power levels and power density required to electrify the big 737 type aircraft and larger, the regional single aisle and larger? We need megawatts of power, and we need the specific power to be above 6.5 kilowatt per kilogram. For the motor, power electronics, controls, everything associated with the subsystem. So each component has to be about roughly 2 to 3 times higher, 13 kilowatt per kilogram type numbers. If you want that type of power today, I should say maybe a few years ago, because people have been working on this already, you think about industrial type machines, the big hunks of steel and copper, thick insulation systems for the high voltage that will be required. That's literally not going to fly, too heavy, right? So that kind of helped launch a lot of programs that we have ongoing here at Illinois and many of our sister institutions. So NASA came in 2014, so almost 10 years ago, 9 years ago, and identified a kind of a sweet spot to encourage electrification of aviation. If you could have a megawatts of electric power, that can impact a whole range of aircraft classes. So they came up with the challenge, and I'm proud to say that Illinois students, postdocs, the teams over here went ahead and built a machine that actually met the National Academy's threshold number in terms of power density. So this is a bulletin out of the NASA team that we worked with, motors that can literally power the future of aircraft propulsion. And not just Illinois, I have pictures here of work by Ohio State, I want to say Wisconsin, several other universities are indeed actively engaged in this research as well. We can't stop there. You can't build one motor and say we are done. Technology is proven. Now everything's solved. So we've gone ahead and worked on integrating this in actual propulsion system. This actually, I was very pleased to see this on the cover of the brochure that you have here. 300 kilowatt to a megawatt propulsion unit tested in the lab, which you can get to see if you walk about 20 feet out of this building here. And looking at how you can scale this machine for various other propulsion units, integrate them inside an engine, get a hybrid electric jet engine. You can do this tail cone thrusters. You can have propulsion units and so on. I also want to highlight that there's a lot of work going on around the country and around the world. So NASA initiated a lot of that work here in the US, but now a lot of these projects have been picked up by ARPA-E. So ARPA-E has an Ascent program, REACH, several others. In Europe, EU is funding a lot of work, Airbus. So a lot of vision vehicles out there on the regional jets and larger. I'll point this out as one of the interesting ones, distributed propulsion, instead of one big engine under the wing. But several people are doing similar work. Going too fast there. So that's already happening. I will characterize all that work as near to midterm. We're going to see this in our lifetime, right? Some of those electrified jetliners. But since you're in the home of John Bardeen, I think he was referenced earlier today, I want to highlight one area we're looking at a little bit longer term and maybe more disruptive, how you can apply superconductivity to have a transformational change in electric machine technology. And I'll introduce this by pointing out this data here. So superconductors is one of those technologies that's been for the future and shall remain there, certainly in the power domain. The promise has been there for at least 30 years since HTS was discovered. I want to say late 80s till now. But there's still no commercial mature product based on superconductors. However, you can go and buy conductors commercially. These lines here are conductor characterized at different magnetic critical fields and critical current densities. So all these are available to us. Compare that to where we design electric machines today. So this is magnetic field here on this axis, current density amps per square millimeter on the other. And if you increase any of this metric in any device that deals with current or field, like a machine, the machine gets directly better. If I double the field, I get double the torque out of the machine. We are boxed in this corner with conventional materials, and this will open up the design space. So we have several activities going on, exploring how this can be applied, how can we make a practical superconducting machine. The catch, of course, is in spite of a recent publication, there's still no room temperature superconductor out there. You do need to go down to cryogenic temperatures. So that becomes the challenge we have to deal with. But there are some concepts out there, and I'll highlight Cheetah, which is being led out of the University of Illinois, a NASA ULI, where you use hydrogen as the fuel source. And if you carry the hydrogen as in the liquid form, as you boil off the hydrogen at 20 Kelvin or so, that becomes a heat sink for a superconducting powertrain. So the dual use could simplify the propulsion system, and we are making little gradual progress towards demonstrating superconducting coils and trying to put them in an actual electric machine and a powertrain. This has now led to additional work supported by ARPA-E. So I will point to some of these targets and connect this back to the report by the national academies. So you want to go from 1 to maybe 10, 11 megawatts to truly electrify most of the large aircraft out there. So this program targets, the number is somewhere here, 5 to 10 megawatts. So really completing all the way to where you want to electrify aircraft, including the transatlantic type larger vehicle classes. Hopefully, if any of you come back in, 3 years from now, we will have one of these motors running on a dyno. I again want to make sure that I point out we are not the only ones working on this. Certainly in Europe, there is a very similar program called Ascend, again a hydrogen-powered aircraft using a superconducting powertrain. Again, baby steps, building coils, testing them in the lab, but they're projecting similar time frame. By the later part of this decade, there could be machines that are being flight tested. And then maybe the last example, not just Europe and here, this is an example out of Russia, who claimed to have been the first to put a superconducting motor on an airplane. It's a little bit of a, it did not fly the airplane, it was put on the airplane and the airplane flew. But it's still interesting just to show that there is a healthy competition around the world. We like to think we are ahead in the US. It's left to be seen who gets to fly one of these first. So I'll end with that. So electrification complemented with sustainable aviation fuel can help decarbonize aviation. I'll let you maybe look through other bullets. I mean, to me, the most exciting thing is at the bottom here. I think this was also mentioned this morning. Electrification is serving as a disruptor in the aviation field, letting students really get their creative juices out, go almost clean sheet designs and come up with novel concepts that fly. So I think it's a great time to be an engineer right now. So I'll end with that. I don't know if you're taking questions. Okay. Thank you. If there is one question.
6 kilovolts on that machine is a pretty scary number. NASA is looking at 1 to 2 kilovolt range these days. How do you feel about that? I mean, could you actually go at altitude? What do you think?
So there's a long answer to that. I'll just maybe say that when we go superconducting, for more than one reason, all of this has to be within a vacuum vessel. We had to thermally insulate it. So the high voltage is inside a vacuum. It's not seeing the ambient conditions. So that's kind of the quick answer, but many, many challenges have to be overcome, of course, right? We're talking about maybe 2030 time frame before these are literally flying. But thank you for that question. All right. Put this over here.
Thanks very much, and I think I should, maybe there's another talk that somebody will get ready. So And our third speaker is Professor Giorgio Rizzoni from Ohio State. He's the Ford Motor Company Chair in Electromechanical Systems, and he's a professor in Mechanical and Aerospace Engineering and Electrical and Computer Engineering. Since 1999, he has been the director of the Ohio State University Center for Automotive Research, ICAR, and this is the I, I'm already biased, you know, we always start with I here. And he is currently leading an ARPA-E project in the Next Car program with the aim advancing energy efficiency in connected and automated vehicles. Thank you.
Well, good afternoon, and I see I'm already on the last slide, so we're in good shape here with time. I will exit and start from the beginning. So a slight change of pace here, and I really wanted to make a quick comment about how much I appreciated the earlier introduction of some of the history. Phil has saved me a few minutes here, a couple of minutes. I had some historical pictures, but I actually have a picture of the same car, the Detroit Electric you had. But let me say a couple of things. This is a change of pace with respect to these presentations in the sense that while I am a researcher in this field and I have worked on electric vehicles for actually about 30 years now, I started with an electric race car that used an AC propulsion drive in 1993, actually. But I'm going to talk a little bit more about the economic impact of this transformation of the mobility industry towards electrification and make some suggestions about where there could be some other opportunities that have to do with translating the technology that we hear about in these brief presentations here into actual commercial products. Two quick words. Center for Automotive Research at Ohio State has existed for a little over 30 years. And we are a cross-disciplinary, cross-cutting research center in the College of Engineering. So there are activities that touch on many different academic departments. And we primarily focus on students, of course. We are a university. We're currently supporting over 100 graduate students on projects that range from vehicle automation and connectivity to electrification, energy storage systems, and the like. And so here is a broad, big picture overview of the things we do. What I like about being affiliated with this center is the fact that all of the different topics that have been brought up in preceding discussions, from infrastructure to electric drive systems to energy storage to hydrogen, we sort of bring all of these things together, and we have fantastic collaborations with other interdisciplinary research centers, such as the Aerospace Research Center, for example, and our friends in the Center for High Performance Power Electronics. So I've had the great pleasure of working with many colleagues on topics that touch on the subject of today's conversation. I'll just make a comment. We've never been as busy as we have been in the past 3 years or so with continuing education, and this continues to grow. I had another conversation yesterday with another company. We need to transfer some of this knowledge to engineers in the industry. There is a great desire, sort of thirst for upskilling in this industry, and I think that many of the things that we collectively do are quite relevant. So the work we do is supported by federal agencies, private sector companies, and I saw reference to an ARPA-E project just a moment ago. That's been a great source of funding and inspiration for us, and also the commercialization focus of those programs is a very important thing. So I was going to say a couple of words about history, but I'm just going to fly by with a couple of pictures here. These are reportedly the first 2 electric vehicles, and they're just drawings, not photographs. But what I wanted to point out is take a look at those batteries on that tricycle. The 12-volt battery under your internal combustion engine powered vehicle looks just like that still today. The other comment, and the one on the right is a photograph. You may not know that in 1896, there actually was a fleet of electric taxis in New York City, in Manhattan. It really only operated for a year because it actually lost money, but they tried. And you mentioned Detroit Electric, I'll mention Baker Electric in Cleveland, and I can't let the opportunity go by to tell you that there was one in Columbus as well. And when I first found that ad for this Columbus Electric from the Columbus Buggy Company, and I looked at the address, I live around the corner from 561 Dublin Avenue. That specific address doesn't exist anymore, but it's in my neighborhood. Okay, so second point that I want to make here after these brief introductions is energy. And many things have been said in preceding presentations about the impact of energy, but I want to present you with, if you will, maybe a bit of a sobering thought on what it is that we really have to do. Some of you may be familiar with these Lawrence Livermore National Lab charts. I use them a lot whenever I introduce the subject of efficiency and sustainability in mobility. If you look at it on the left-hand side, you have all of the primary energy sources from solar, nuclear, hydro, wind, geothermal to natural gas, coal, biomass, and petroleum. And numbers have already been quoted today where you understand that a substantial percentage of the energy supply in our country is still carbon-based. What I think is very important to understand is when you look at the 4 boxes on the right-hand side, residential, commercial, industrial, and transportation, when you group things this way, transportation is the largest energy consumer, and in 2011, it was something of the order of 95, more, some such percentage dependent on petroleum. So I like to show these 2 pictures in quick succession because here's 2021. So this is the most recent published chart. Sometime in the next few months, Lawrence Livermore will publish the 2022 data. And what you observe here are, first, transportation is slightly less dependent on petroleum, maybe from 96 to 92%, something like that, but still very heavily dependent on petroleum. And my point here is that we need to make up for an amazing amount of energy. This is really a substantial amount. I'll grant you that electric propulsion is much more efficient, so it's not 1-for-1, but still. The second point I want to make is take a look at electricity generation, and this is the good news. If you look at what we had 10, 12 years ago, you can see that eyeballing it, 60% of electricity production was carbon-based, coal and natural gas. Today, that number is maybe as low as 50%, and this is, of course, the nationwide grid power generation mix in the US. But when you look at that electricity generation box, you can see that coal has been largely replaced by natural gas, and wind is actually a significant fraction of the total. When you look at wind being order of 3.5% of the total energy supply for the United States, as I always like to tell my students, you know, you can run Belgium and Luxembourg with that. So it's a substantial amount of power. So good news is we're doing a good job on the grid. We need to do more of that, and generally speaking, we need to become more efficient about things. And if all else fails, I have a perfect solution for you. Here is a sustainable biofuel-powered vehicle, net zero carbon, pretty close to net zero carbon. You still have to beat those horseshoes into submission, okay? And not zero tailpipe emissions, unfortunately. But it's only 1 horsepower, okay? We should be able to do a little better than that. So let me tell you then about the story of a program that we're building. And this is a summary that I prepared for a workshop of this core team. The core team is made up of the 5 universities that you see there, and some of the Purdue colleagues are actually in the room today. And the idea of this electrified mobility innovation engine was to address the context. EV adoption is clearly growing, and we all understand in this room, we certainly agree that this is something that is happening and must happen. But there are some challenges. There are critical barriers that range from customer acceptance, the availability of vehicles, and by the way, the supply of certain materials for battery production is becoming to be a challenge these days. For example, nickel. Russia produces 60% of the nickel that is used in the world, so that's becoming a precious commodity. Cobalt, we all understand that that's a very valuable and not easily available material. And so there are many challenges, and the conversation about lithium is another long one that we could have maybe at dinner time. But it's not only that. If the industry is to transform itself to really be ready for this transformation to electric mobility, and I've had the good fortune of working also on some aerospace programs funded by NASA, so I have a small beginning of an understanding of what the air mobility side of things is like. We have to prepare the workforce for tomorrow. So about close to a year and a half ago, we started a series of workshops with partners in 5 states. You can see what the 5 states are. And the decision to concentrate in that particular area is based very much on this map, and there are many maps that show you where engines, transmissions are manufactured, where automobiles are assembled. And about 75% of that industry is in this, let me call it the automotive Midwest, with about 500,000 manufacturing jobs and about 4,000 firms that are tied to legacy component production. These are the companies that make gears and valves and pistons and the like. So where is that going to go? Are we at risk of displacing a generation of workers, and how do we prepare the next generation of workers? So the idea that we have developed is to create an electrified mobility innovation engine that has basically the structure of being an independent, nonprofit organization that links business, universities, government. It is an intellectual property holding subsidiary to enable for a more agile translation of innovation to market. And it is supported by an venture studio model fund that is available to provide investment in technology development. So the idea of this organization is to deploy public and private funds, strong support at the state level in each of these states. And the idea is to, in parallel, work on technology innovation, but also on creating workforce development programs that will appropriately reskill, upskill, and train from scratch new generations of workers that are really prepared to address this revolution in the automotive industry. You know, there is a piece of my background that wasn't immediately obvious, but I did my studies at the University of Michigan, and I then spent the last 30 years in the state of Ohio. These are like the #1 and #2 automotive states in the country, so my whole head has been full of auto industry ever since I was a graduate student. So to me, this is an important mission, and I have a pretty good understanding, actually, of what it means for a company to shut down, and I think you understand that. The automotive plant moves out, and all of a sudden, the livelihood of an entire community is gone. So how do we keep our region productive and fully employed in this region? And so the idea is to focus on transformative technologies that have to do with all of the bits and pieces that are inside and around the vehicle. Important recognition that infrastructure is as important as the technology that goes in the vehicle itself. And then how do we influence, how do we shape policy, and how do we support workforce development? So the idea of this electrified mobility innovation engine is to act as an organization above the parts that tries to bring together the business sector, the investment fund sector, universities, and professional societies, K through 12 communities, to essentially execute a program through which R&D that is conducted at our institutions, for example, can be rapidly commercialized and translated into products easily licensed to existing companies or lead to the creation of spin-off companies, and that there is a regional strategy to how to address workforce development in this area. So as I said, we spent close to a year and a half developing this model, and what you see here is a color map of organizations that are part of this emerging network. And they represent community and technical colleges and vocational schools, trade and professional societies, the innovation sector, federally funded research lab. You have Argonne National Lab a short distance away from here, but in this region we also have Oak Ridge National Lab, the Air Force Research Lab at Wright-Patterson Air Force Base, NASA Glenn, Crane Naval Research Operations. There are the, what used to be called the Tank Army Development and Engineering Center, TARDEC. Industry, universities, and state agencies. You know, our states are all very concerned with workforce development. How can we help them implement some of the programs they would like to implement? And the structure of this organization is such that it is going to be run in a very lean way as a nonprofit LLC with a CEO who has significant industry background and a strong board of directors that is made up of participants from the core universities that have created this concept, and then expert members who may represent state government, national labs. There is a mix of experts that act as the board of directors for this company. And then the partnership network will guide the activities of this organization to essentially seed technology development programs in all of the areas that have been mentioned so far: superconducting materials, non-rare earth permanent magnets, new materials for batteries, new ways of developing cooling and thermal management systems for all of the above. And the idea of this program was born at a time when we thought that the U.S. Department of Commerce was on the verge of announcing programs in this area. It turns out that didn't happen. It has happened more recently, but at that time, the first program that came up with a sort of funding structure that might be appropriate for this was the NSF Engines of Innovation. So we have applied for this program. I'm sure that many other people in this room have participated in some NSF engine proposals. This is, I think they received 120 Type 2 submissions. But aside from the NSF part, this is something that is moving forward. There is sufficient interest at the state level, and we've actually already created a venture fund that is specifically dedicated to investing in these technologies, and we've attracted some private capital. We're hoping to grow that in the near term. And I know that, I was a little bit embarrassed in the sense that I show you this picture of the automotive Midwest and the state of Illinois is not in it. Let's talk. I think that we're close enough, and certainly from what I've seen today, the spirit is there. And I am sure that it's not too difficult to expand the region that is relevant to the automotive industry, but you have to start somewhere. And so this is the team that has started the program. And I'm hoping that later this afternoon and during the course of the evening, perhaps we can have more conversations about this. Thank you.
Final presenter, and I'm not going to touch this again just in case I do the same thing as I did before. So we welcome Ria Kontu, who's an assistant professor in our own civil and environmental engineering department here at Illinois. Her research interests are in sustainable transportation systems planning and operations, and her group develops quantitative models and data-driven solutions to emerging electrified mobility challenges. And she's an alum of the NAE Frontiers of Engineering program. So Ria, I don't see her. Oh, she's over there. I was looking in the wrong direction. She's going to talk about electric vehicles and charging infrastructure systems.
Okay. Hello, everyone. Thank you for the unique opportunity to be here. It's actually an honor to be part of this group of eminent speakers and members of the audience. So thank you for having me. I would like to start by saying that I'm excited to talk to you about electric vehicles, charging infrastructure, and provide some research insights on adoption, deployment, and management of these electrified transportation systems. We know that our own and the next generation of engineers will work towards making it happen, right? Building, managing, and maintaining these electrified transportation systems. So we hope that they're going to target improving the quality of life for all as they do. I hope that at the end of this presentation, we're going to have time to discuss your own ideas on how we can make the challenge, the grand challenge of transportation decarbonization be tackled. Transportation has the highest share and reliance on fossil fuels of any sector. I think many of the speakers make that clear. In 2021, it has accounted for 37% of global carbon dioxide emissions from end-use sectors. Addressing the climate crisis and mitigating the significant risks that are posed by climate change requires an important reduction of transportation emissions. And making sure that we reduce also its harmful pollution. However, we need to think what powers transportation, vehicles, massive shifts to new technologies, cleaner technologies such as battery electric vehicles, also hydrogen, sustainable liquid fuels for the light, medium, and heavy-duty sectors are crucially important. And they are part of the decarbonization portfolio, but they are not a panacea, right? We need to think beyond vehicles. We need to think about travelers' attitude changes towards active transportation and electric public transit. We need to think about infrastructure that supports safe and effective operations of multimodal transportation systems, clean electricity, as well as effective travel demand management, right? A major engineering challenge is planning and implementing the transition to transportation decarbonization. And this incurs implementing new objectives. These objectives need to address the disparities, the disproportionate energy and air quality burdens that disadvantaged and underserved communities are facing, making sure that as we deploy these technological advancements, these innovations, we distribute the benefits in an equitable manner. This is crucially important as we are facing the next decades of this transition. We know that the transportation system and our communities are threatened by worsening and very frequent climate impacts, such as hurricanes, wildfires, extreme floodings. They're happening more and more frequently nowadays, right? So engineers will need to take up the challenge to design these resilient and sustainable transportation systems and make sure that they fortify the infrastructure that powers them. Let's go to some of the statistics that I have in this presentation. We know that the average household in the United States spends almost 20% of their income on transportation expenditures and 4% on fuel costs. Transportation energy use facilitates access to a wide array of opportunities. These opportunities are tied to economic, professional, educational, recreational, and social in the US sprawled and car-oriented environment. Long commuting and high fuel prices can impose burden to meet household travel needs and raise the share of transportation expenses relatively to a household's income. Transition to electrified light-duty vehicles has real benefits that are not only tied to reduction of emissions that frequently depend on the marginal electricity generation mix and the marginal emission rates of the region's grid, but are also economic benefits. In the state of Illinois, when shifting from a gasoline to a battery electric vehicle, the decrease of pounds of emissions over a year is approximately 82%. Even though in the early stages of the transition, we will have electric vehicles that have higher capital costs compared to their gasoline counterparts, we know that there are economic savings that can accrue over the lifetime of the vehicle ownership, since electric vehicles have higher efficiencies and they can charge with lower electricity rates, lower electricity costs. These could lead to more than 50% fuel cost reduction over a year and 30% lower maintenance costs, signaling opportunities for consumers that go beyond the altruistic satisfaction of the reduction of environmental pollution when owning an electric vehicle. These costs and environmental externality reductions are actually, the benefits that we accrue from these are actually translated to sales. Plug-in electric vehicles that include battery electric vehicles or EVs, as you can see in this graph, or include also plug-in hybrid electric vehicles. We know that in September 2022, it was the first month that monthly sales of new plug-in electric vehicles reached 7.4% of all light-duty vehicle sales. Of these, 6.2 were attributed to battery electric vehicles and 1.2% to plug-in hybrid. From the introduction of plug-in electric vehicles in the mass market in 2010, it took approximately a year in order to have these monthly sales exceed a 2% share of all vehicle sales. A decade was also needed in order to build a tremendous network of charging ports, electric vehicle charging ports. You can see in the graph on the right-hand side that in 2022, these exceed 140,000 ports. The predominant public charging level is level 2, while we observe steady investments in the growth of a direct current fast charging network in the United States. Maybe this is a good time to pause and ask a question to the audience. How many of you own electric vehicles? Okay, a few hands are up. What is the most frequent location of charging your vehicle? Is it home? Yes, I see a few hands up. What about people that charge at work or campus? A public location, a Tesla supercharger? Okay. Okay, I see. The majority of people here charge at home. I think it is important to note that to tackle the challenge of planning for electric vehicle charging network, engineers need to use empirical data from either revealed preferences or stated preferences, either from early adopters or prospective adopters, respectively, when they are planning for these charging locations. Here we use data from a California Energy Commission survey that shows that 88% of the battery electric vehicle drivers had charging sessions at home, something unsurprising given the convenience of several hours of overnight vehicle dwell time at this location and the lower charging expenses. 24% of the early adopters had a session at work, while only 17% mentioned using fast charging at least once, where charging sessions are faster, but costs are actually higher. Can home charging be a ubiquitous solution? I think I am delving into the places and areas that Phil tried to allude previously, and he was very successful in doing so. I think, from my perspective, I think, yes, it is possible as long as we recognize that there are certain residents of housing types that would need new solutions, management solutions to help them access charging infrastructure and also have opportunities to use them effectively. Only 1/3 of multi-unit dwellers have access to garages where charging infrastructure can be effectively installed, compared to 2/3 of single-family unit residents. We know that in these apartment complexes, cost burden, renters' rights, and ineffective shared charging management can actually hinder the multi-unit dwelling chargers' deployment and ease of use. When charging at home is not an option, electric vehicle owners will face higher charging expenses and an increased probability of not meeting their desirable state of charge at the beginning of their driving day. This is a crucial charging equity issue and an equity problem that we must address. My group, using Department of Energy Vehicle Technologies Office funding, introduced the concept of community charging hubs in multi-unit dwellings, where we envision that multi-unit dwelling parking lots will host a limited number of chargers that are actually shared and can be of similar or different power levels, while the residents' charging schedules are managed, accounting for their travel patterns and adhering to their daily schedules and their constraints. Such a shared charging management scheme can perform dynamic charging session to station allocation and help right-size the infrastructure that is deployed in the multi-unit dwelling, making sure that it supports the residents' needs, while also maximizing the charger's utilization and the return on investment of the investor that pursues this venture. We need to perform techno-economic assessment in order to be able to understand what is the levelized cost of charging under different ownership models. And you see here that we have explored residential, utility, and private company ownership. We are assessing the trade-offs between costs and performance of the charging hub. For example, we see that in Los Angeles, a homeowners association that is operating a typical multi-unit dwelling, an average multi-unit dwelling charging hub with 8 level 2 chargers, will have residents incur costs of 38 cents per kilowatt hour with an average waiting time of 40 minutes to charge. However, if we implement 13 level 2 chargers, we're gonna see a 13% increase in the levelized cost of charging, but virtually zero delay for the apartment complex residents to charge. So understanding these trade-offs dependent on the location becomes important in order to make these investment decisions. If the prevalence and the importance of home charging are undisputed, then what is the value of public charging infrastructure to consumers? I believe that a dense network of public chargers assists electric vehicle travelers to extend their electrified miles, cope with range anxiety, which is the fear of exhausting the vehicle's driving range before reaching a destination or a public station, and complete their long-distance trips. So public chargers can also have spillover effects, increasing and building the confidence in the future of the plug-in electric vehicle market, as well as expose travelers to this new emerging technology, which could increase consumers' willingness to own this emerging technology. Our case study, based on California's public charging network in 2017, showed that to a purchaser of a new battery electric vehicle with an 100-mile of range and home charging access, the network of chargers, fast chargers actually, across the intercity routes is valued at more than $6,500 through our willingness to pay analysis using real-world data. How do we plan for these public chargers locations? I think this is an important question. I want to point out that charging infrastructure facility location models have actually shifted from a more cost and economic-centered focus towards a more multi-objective, multi-stakeholder consideration. We know that nowadays these locations need to be responsive to multi-stakeholders' feedback and insights that come from network providers, the economic viability of the network, utilities and their electrical upgrades, their costs, as well as their timing, as well as equity, which is multifaceted, and it's also valued more and more from public agencies. For example, distributive equity could be aligned with environmental justice objectives and assessed by evaluating emissions across different regions. In our analysis in the state of Illinois, we actually used a lot of data that are related to economic, social, and environmental justice factors. We accounted for charging, current charging inaccessibility, household incomes, traffic proximity, substation proximity, particulate matter 2.5 concentrations, as well as the location of minority and disadvantaged communities in order to help the state make the decisions of how the benefits are distributed in an effort to provide a more holistic assessment of the placement benefits. We were successful in integrating also voices that come from different interests in that area. So charging providers, utilities, non-government organizations, and public agencies all were integrated in this process through a 50-member EV steering committee, electric vehicle steering committee of diverse interests. As we envision an electrified transport future, and I think that this is something that we are not always remembering, we expect a massive retirement of gasoline stations and their supply chains infrastructure during the next decades. Planning for phasing out the fossil system until the new clean energy system is ready to take over is imperative for both safe and reliable transportation operations. The two systems will coexist likely for several decades, and the climate change will induce them to operate beyond their design parameters. Our engineering graduates will have to manage transportation and energy systems that will probably operate suboptimally, as we're trying to optimize for these two systems. They're taking more and more space during the transition. And as we're moving away from a stable fossil-fueled transport world, and we're moving towards a new transportation equilibrium, an electrified transportation system that is powered by clean energy systems and technologies. So planning and working with public agencies and communities to actually come up with technological and management solutions that are relevant to their needs is the new standard for successful electrified transition. We know that EVs are 3 times approximately more efficient than their gasoline vehicles counterparts, but overall greenhouse gas emission benefits, reduction benefits depend on the electricity generation mix and its carbon intensity. It is vital for utilities and charging network providers to enable households and commercial users to actually use renewable energy for their electric vehicle electricity needs. And promote charging at times that assist with integrating more renewable sources on the grid. Time of use and dynamic electricity tariffs can incentivize clean energy use, and smart charging management can help better align charging timing with renewable sources availability. We know that solar arrays and battery energy storage resources that are co-located with these fast charging stations can help mitigate high costs from demand charges that are incurred by charging network providers with electricity that is generated from these photovoltaic systems. Resilient community microgrids can be important in areas that are prone to extreme events, ensuring the service of critical loads during, for example, electric vehicle evacuations. Talking about evacuations, evacuation planning is crucial in achieving resilient and safe communities, particularly in the face of natural and anthropogenic hazards. Only in 2022, there were 6 hurricane and tropical storm disaster declarations in Florida. Actually, one lesson that we learned from Hurricane Katrina and the adverse events is that evacuation route planning is helping streamline the evacuation process and can result in avoiding delays in reaching shelters. So it is important to think how all these systems are going to be adapted for electric vehicles. Electric vehicles might be facing sparse charging infrastructure networks and evacuation distances that exceed often the actual driving range of their vehicles. So this can pose challenges to the travelers reaching safely shelters. A major engineering challenge is to provide designated paths to electric vehicle evacuees that enable safe routing alongside access to charging infrastructure. To tackle this challenge, our group developed an optimization framework and its solution algorithms in order to designate optimal evacuation routes that guarantee access to charging infrastructure for electric vehicles, while taking into consideration the needs of the rest of the transportation network users. Here you can see evacuation routes that are designed for the South Florida network, transportation network. Beyond just routing vehicles, strategically placing charging stations can help reduce short-range electric vehicles' vulnerability and improve their evacuation clearance time, particularly before imminent disasters where we have these preemptive evacuation orders. Emergency and portable charging stations can be a solution to this emerging challenge, and our group formulated a new location routing problem to support charging needs of electric vehicle evacuees in this manner. We were able actually in the Florida network to specify the nodes of the transportation network that these emergency chargers would need to be placed at to assist with faster evacuations and clearance times. Last but not least, climate change is driving an increase in the advent of power outages. So thinking about all the adverse effects of climate change on the occurrence of evacuations, we also have power outage events that are disrupting the grid infrastructure. Well, we have a next generation of electric vehicles that are equipped with bidirectional energy exchange capabilities, such as vehicle-to-household technology. This provides opportunities to ensure that household electricity demand can be partially served with the vehicle's battery resource. Such bidirectional connectivity can be vital in avoiding health hazards caused by cold temperatures or overheating during these power outages. We have done simulations, extensive simulations across different climate regions in the United States. You see a graph here from the South US climate region during the summer, where an electric vehicle such as a Ford F-150 with a 50% state of charge can cover the residential energy needs during a 12-hour power outage with a 90% probability. These types of vehicle-to-home connectivity can be coupled with residential energy modulation to ensure that its battery resource can be a viable solution against short-term power outages during either cold stresses or extreme heating events. And I reach the point of conclusion. I would like to emphasize that all these technological and societal challenges that are relevant to planning and operating sustainable, resilient, and equitable transportation systems would need to be effectively solved in the next decade if we are to be on track with our decarbonization schedule. Engineers are at the center of this transition, and it is our duty to instill to the next generation of engineers and the workforce of the future all the principles so that they can develop these technological advancements, management strategies that serve and respect real community needs and are adaptive to the very real risks that are posed by climate change. Thank you very much.
Anything, any simulation or figure out as the market penetration increases, more people will be coming to charging station. How much they will have to wait? Of course, it will depend on where you are, but as far as Illinois is concerned, with your network, have you done anything like that?
Great question. I think if I understand correctly, you're asking, as we are seeing more and more electric vehicles in the market, right, where you expect to see queues being created in the existing charging stations, right? So I think that This is not something that we are seeing currently. So currently the utilization of public chargers is actually relatively lower than what we would expect to be, and this is actually a concern for the network providers. But there is room via management when the demand becomes significant, right? Via right management, smart management systems to be able to have a positive experience while also meeting the needs of the drivers. I think that the charging scheduling problem can be solved across different dimensions, since we have opportunities to charge at home, work, during other activities that we pursue over the day, and in intercity trips in these very fast charging stations. So you're right. As we are expecting to see more and more demand, the number of ports should also grow in order to accommodate them if we end up seeing these long queues being created in charging stations. However, in the type of analysis that we've done at the moment, we are not seeing significant queues being built up.
So a question. I'm curious as to what we can do with zoning and other kinds of requirements. I mean, is it realistic to say, okay, you multi-dwelling owner or you condo association, if you're above a certain number of units, you're required to install an electrical outlet within 10 feet of every parking space in your unit. Is that rational, or is that just ridiculous?
I think that's what the city of Chicago aims to do, right? They are aiming for all new constructions to make sure, dependent on the size of the dwelling and dependent on the size of the complex, to have a certain share of the parking lots be electric vehicle, be places for electric vehicle charging. So already cities are working towards making sure that these apartment complexes are configured in a way that installation can be fast and easy, compared to a case where renters would have to reinvent their wheel and manage this very complex space.
Okay, and I hope if there's anybody here from campus, you know, there's a new parking structure going up at Pennsylvania Avenue and 4th Street, and I hope that they're going to put an electrical outlet at every space in that parking structure. We'll have to keep on them, I think.
Somebody's taking notes. So there are no other questions. Thank you very much.
Thank you.
He holds the Granger Distinguished Chair, and he is a professor of material science and engineering. He also has co-appointments in several departments across campus, including chemistry, mechanical science and engineering, chemical and biomolecular engineering, and he is also a faculty member in the Beckman Institute. Paul has been working on fast-charging batteries for a number of years now, and I think he's going to give an exciting talk on resources and materials from extraction to recirculation. So I'm excited to hear what Paul has to say. Thank you, Paul.
Thank you, Nancy. It's really a pleasure to be here, to have the opportunity to talk to everybody. I think we've heard through some really great talks through the morning and into the afternoon, just how electrification is really going to impact and is impacting virtually all segments of society. I think we recognize that storage is a significant component of that. It's not the only component by any means, but it's a very significant component. And so hopefully I'll be able to talk to you for a little while now about sort of materials, new opportunities in materials ranging from issues in extraction to recirculation and reuse. Okay, so probably you've all seen this, so I'm not really going to spend much time on it, but if you look at the battery that you have in your pocket or your EV, they virtually all look the same. There's a few other variations, but most of the world is using a battery which looks a lot like what we see here, which consists of a carbon-based anode and then a transition metal oxide-based cathode. And what's simply happening as you charge and discharge, lithium ions are moving back and forth, and electrons are moving through the external circuit. That balances the charge. And the voltage that comes out of the battery is really the energy difference between lithium or close to lithium and the lithium salt. And this is why if you take a piece of lithium and put it in water, it reacts violently. Actually, sodium more so for a variety of other reasons, but we don't need to go into all the details. And if you go ahead and put lithium salt in water, virtually nothing happens. It simply dissolves. So that's the difference in the energy. So you can almost think of a lithium-ion battery or some emerging lithium concepts. When we charge it, we're just putting the lithium in the high-energy state, and when we discharge it, we're putting the lithium in the low-energy state. One of the challenges in this system, actually, is that the volume or mass, and certainly volume and somewhat mass fraction of the materials that's actually participating directly in the storage is relatively low. There's a lot of balance of system, even in the individual cell, and that doesn't account for what happens when we go to packs and larger systems. There's a thin polymer membrane, and if it fails, your battery may explode, so you want to be somewhat careful about that. There's, of course, current collectors, so all the internal wiring. And then most batteries today, the lithium isn't as a metal. It's actually intercalating between carbon sheets, where you have 6 carbon atoms for every lithium at best. And at this side, we're basically bringing lithium in and out, and we have metals which are relatively heavy along with oxygen and other components. So we really could do a lot better. So when you look at those charts of where we are in energy storage and the theoretical energy, if we could actually use lithium as the energy source, lithium is actually a very high energy source. It's not that far from oil. The problem is all the system that's necessary to extract that energy in a useful way. Okay, so what are some of those systems? So if we look at the cost breakdown, there's a variety of what I'll call higher cost materials, lithium, nickel, potentially cobalt, copper, the electrolyte, as well as others that we can call lower, but some of them are still reasonably expensive. Manganese, and iron, probably not too much of an issue there. Graphite, which is more expensive than you might think. Aluminum, and then sort of some high-value organics. And so if we look at the cost breakdown, and these numbers move a little bit as costs go up and down for raw materials, but lithium, nickel, cobalt, copper, we're approaching half of the cost of the battery. So if we can drive those costs down, we will reduce the cost substantially. And that's why you're hearing about batteries today that maybe are lithium iron phosphate, which is now used in some electric vehicles, because of course the costs are much lower. But that still doesn't solve the problem, for example, of the need for copper, lithium, and then a variety of other costs that sort of layer on top of that. So let's look at the inside of the battery, then where are these parts? So If you take a battery and cut it in half, and it's not advisable to do that unless you've paid a little attention to how you're going to go about doing it. But if we take a battery and we cut it open, you'll see that it often looks like a jelly roll. This is a fairly standard configuration in the inside of a cell. If you zoom in a little bit, you'll see that there's copper sheets, which are the negative terminal. There's aluminum sheets, which are the cathode or the positive terminal. Attached to the copper is graphite, along with some other ingredients to hold the graphite together. There's this thin polymer separator. If this fails, you have a big problem. You want that to be as thin as possible, but it's not storing any energy. So if it's thicker than you need, you've wasted certainly volume and a little bit of mass. And then in your sort of classic, for example, cell phone, laptop, or some of the early lithium-ion-based EVs, lithium cobalt dioxide, which has now largely been replaced in transportation with lower cobalt systems, but most are still not zero. This is filled with that liquid electrolyte, and then of course the whole thing is full of binders. So I think of a little bit of it this way. Imagine that we made solar cells and we took it by grinding silicon up into tiny little chunks and mixing it together with carbon black and polymer and painting it over the surface and expecting that we had a high performance material. You know, we wouldn't have that. But that's really where we are with, I think, batteries today. We take what could be high-performance material, we grind it into a powder, we mix it with other ingredients, actually, in things that look like industrial kitchens, and we paint it over surfaces. And we lose all the advantages that could come from the material science, the crystallography. You know, we add defects into the structure. So my vision or hope would be that, 50 years from now, people look at it and say, why in the world did you do it this way? But that's what we have today. But I think there's really a lot of opportunity. When you'd say, where are we in energy and power? There is a lot of room to grow if we just learn how to grow better materials, how to use the right materials, how to control them, and take advantage of all of their properties. Again, if we just zoom in, and again, you'll see now the positive terminal, it looks like basically sand particles. In fact, I have a completely unrelated project on soil engineering with some people who are actually here in the room today. And this looks a lot like what you would get if you took sand and you make a sand castle and pack it together, except we add other components. And so this is now the cathode, separator, graphite, and then other materials, additives, et cetera. Okay. So what are the challenges? Well, there's a few challenges. One, of course, is that what if we run out of lithium? Well, there is a lot of lithium around the world. The question is just what is the availability and the cost to extract it? And I'll just talk specifically about some new emerging concepts in lithium extraction. And this has come about because when we look at geothermal brines, there's enough lithium in the geothermal brines in the US to be a major contributor to the lithium supply, if we could figure out how to effectively extract that, which, by the way, we're already bringing all the brine out of the earth, so we actually wouldn't need a new mine for that. We would use today's geothermal extraction. It's not the only issue. There's cobalt and nickel. We've already heard about issues with nickel, cobalt, of course, also. There was going to be a new cobalt mine that was supposed to open in the US, and just in the last few days, they decided not to open it due to cobalt prices fell a little bit, and the economics just didn't make sense. That may change. But there are other chemistries mentioning, for example, lithium sulfur, people have talked about. So there may be other ways, but you'll see that lithium sort of remains prevalent in all of these systems. But maybe there are new concepts. For example, work on solid-state batteries. If we go to a solid-state battery, maybe now the anode is lithium metal, so we get rid of all of the carbon. And possibly on the cathode side, we can also get rid of some of the materials. The separator might be much thinner. You're not going to find these today in any large production, but it's, I think, a very important target to consider. This eliminates the need for many, the liquid electrolyte, separator, graphite, polymer binder, maybe cobalt and nickel, but there's really major technical challenges. And finally, recycling. Maybe that's not an issue today, but we have a lot of EVs going into the fleet. In 10 years, we're going to have a lot of EVs coming off of the fleet, and we need to be prepared and ready for that. And they're actually going to be full of really valuable materials. I think an interesting perspective, lead-acid batteries today, your starter motor batteries, are recycled at 99%. we are going to recycle lithium-ion batteries or lithium batteries and EV batteries, whatever chemistry they're going to be. We're going to recycle them at 99% as long as we make even a modest willingness to go ahead and do that. It would be crazy to throw those into a landfill. Forgetting the environmental, I mean, they're basically gold. You know, people are going to want them. The key is now going to be able to do that in a way that's environmentally responsible and in a way that the economics are viable. So let's talk a little bit about the lithium extraction from brines. So this is what's being already done, is you take a hot brine out of the ground and you inject a cold brine back into the ground. The lithium concentration at the Salton Sea is about 180 milligram per liter. That's one of the higher concentrations. So we need to figure out how to extract that. There's many other ions at higher concentration, so it is a challenging separations issue. And the brine is hot. If you take that hot brine and you put a classic battery electrode in it, it's going to go away. But think about what a battery electrode is. It's a material that can suck up lithium and release lithium on electrochemical potential. So, you know, what we've been working on is, can we take and in essence put battery cathodes and extract the lithium and then take those same cathodes and release the lithium. And there are compounds where lithium atoms will fit, or lithium ions will fit, and sodium and calcium and iron and magnesium and et cetera simply don't fit. So I think there's every reason to believe that we can create materials that will very effectively take up lithium. They'll use a tiny bit of electricity in the process, which, by the way, you're sitting at a generating plant, so that's, if you want to use it, that's not a bad place. And do it over a really long life, as long as we can figure out the right materials. So we've been specifically working on making a ceramic membrane. It's lithium cobalt dioxide. And lithium cobalt dioxide, the cobalt's a little expensive, but if you're able to use it for many months, it turns out that the cost per lithium atom is almost negligible in the system. The advantage is that in lithium cobalt dioxide, the lithium atoms fit extraordinarily well. But virtually no other atoms will fit into the structure. So in fact, you can put this in sodium chloride and try to cycle it, and it basically stops. The sodium will go into the top 20 nanometers or so, and that's the end of it. And so there are steps, but all the chemistry actually works out. You can suck lithium out of brine, and in fact, just last week, I walked into my lab, and there was a big Erlenmeyer. I mean, normally I don't have this. It was a 8-liter Erlenmeyer flask full of this orangish liquid, because we actually have a synthetic brine that we got from the Department of Energy that we're now doing tests on. So what is the idea here? Well, this is your usual cathode, and I'd argue if you put this in brine, eventually it's going to fall apart. The carbon's going to react. It's going to get fouled. So what we've been able to do is we've been able to electrochemically grow a solid lithium cobalt dioxide and orient the crystal planes, basically create highways that the lithium can come in and out of. And to go to the details, I know there's some electrochemists in the room. We've been able to show first in what I would call version 0 that we could extract and release lithium out of aqueous lithium chloride solutions. Version 1 is a little bit more recent, so this is now in more realistic temperature conditions, but not realistic flow conditions. Also where we're able to extract and release lithium now out of a little bit more complex fluid. And what we're doing now is what I'll call version 2, where we're bringing in brine, flowing out what will hopefully be depleted brine, and then in the cross stream capturing concentrated lithium salts. And so this is the real reactor, and I think actually we have that one out of CAD into now a machined format. Okay, so that may help us with lithium. You know, there's only so many things that you can do well, so we're pretty good at growing these highly textured, dense ceramic materials. They're also what we think is an important enabling in solid-state batteries, which basically eliminate a lot of the other components, because now we talk about having a cathode that's actually oriented to allow the ions in and out versus a long torch. It's sort of the difference. Actually, this room here is a pretty good cathode. Each table here is an active particle. And if you want to get from the front of the room to the back of the room, you have to weave your way around the tables. But what you can do if you grow materials, and the metallurgists have known this for a long time, if you grow materials properly, you can organize the crystal planes in one direction. So now you have very fast paths, low tortuosity. And that's really what we've been doing in the lab using our materials chemistry. Here's a thinner version, but we simply align the planes. And so we are not to the silicon single crystal here, but we're at the first step. At least we've oriented the crystal lattice to be useful, and we've gotten rid of a lot of the material that doesn't matter, the binder and the conductive additives. This is a bit of a special case. I won't say this works for every battery material. We're doing this in lithium cobalt oxide, the one that I told you we don't really like. It has a high electrical conductivity and a high ionic conductivity. But we actually have okay results with lithium manganese oxide for the experts in the room. That has some other challenges. Its electrical conductivity isn't that good, but if you orient it, it turns out it's better than you think, and it will cycle at what one can consider to be reasonable rates. So again, we have a very high density of active material versus a lower density. And now to really go in the weeds, what you're seeing here, this is a special picture that shows you which way the crystals are oriented. And basically what we're seeing here is that these crystals are all oriented so that the layers are running one way. If you take a powder, of course, they're going all different directions, some of which are oriented in a great direction for allowing the lithium, but some of them are absolutely the wrong way, which means now the lithium has to go an even longer path, which costs you more in the way of energy and power. So this is getting into the weeds of what my group does, is trying to really understand how to grow these materials and use these materials in sort of engineering form. And so we're part of a DARPA program here that's now working on building batteries out of this using a lithium as a current collector. The solid electrolyte's a little tricky. One actually has to use two materials probably because one has to be stable with lithium. But again, if you're an electronic materials person, building multi-layers is pretty standard, and so now we can think about doing that. Only one of these layers has to be thick. The other one can just be thick enough to stop electrons, so it can be a few tens of nanometers. And then that's up against the cathode. And since the cathode is ceramic, now you can take this and use standard high temperature processing and all the things that we as material scientists love to do that isn't always compatible with liquid electrolytes and organics. And so I thought I would just show you this. One of the big challenges in solid state batteries is usually you have to apply a lot of pressure because you can't have the layers coming apart. Using these materials, we actually have demonstrated now a zero stack pressure solid state battery. And so that's running here. It's running at about 1 milliamp hour per square centimeter, which is not a bad current density for sort of a handheld a device. So that LED is running at about 1.5 milliwatt, maybe 2 milliwatts, and that's about 2 square centimeters. And the capacities are good. The fade is pretty bad. That's cycle 1, that's cycle 2. I think you can extrapolate where we're headed. So we have some work to do. When we apply stack pressure, it actually works better. So that's what we would call research. But I think we're going to get there because we're using materials that have entirely different form factors. And it's really thinking about how to change the paradigm from these slurry cast systems to using dense materials that are well organized. Okay, so even if we can do the solid state, recycling is what's now going to hit us in 5 years or maybe 10 years. So how are we going to do this? A battery today is a mess. There's carbon in there, there's polymer in there, there's liquids in there, there's fluorinated compounds that who knows what's going to happen longer term, whether those are going to be continued to be allowed. There's, of course, metal oxides, some of which are heavy metals. And so this is how we recycle today, or at least one of the proposed mechanisms and a whole series of separation processes. But maybe we can simplify this. Well, one way, of course, to simplify it is to simplify on the front end. Maybe we should design a battery thinking about what the recycling challenges may be. And there I would argue something like solid state has a lot of advantages. It doesn't have a lot of those problems. But I think we all agree we're not going to be driving around with those in the next few years. So I think we have to be realistic. But if we can go to a solid state, it simplifies the recycling. But one we've been really intrigued with, and it actually doesn't have to be solid state. We learned how to deposit lithium cobalt oxide. We actually do it by an oxidation reaction. Well, in a lot of electrochemistry, if oxidation drives a reaction one direction, reduction will probably drive it the other way. That's not always true, but it's often true. So it turns out if you take a lot of these battery materials, you can actually put them in the same bath that we grow our material from, reverse the current, and dissolve that material. And it only dissolves the material that is the active material. Carbon isn't going to participate in the process. And so what we've been able to do in our group is we've actually been able to take battery electrodes and use them as either as the working electrode, dissolve them, and then deposit new battery material on the counter electrode, which has now been refined and purified. So again, not an uncommon process, but one that I think so far hasn't really been utilized the way that it could. And here's just some examples. This happens to be, these are two batteries. We took a battery, cycled it for a while, dissolved it into the bath and grew a new battery. And I'm not quite sure why we have some issues in the beginning, but after 10 or 20 cycles, it virtually behaves the same. So I think we really can think about not just sort of recycling the traditional way. I think we can head to the paradigm where over time, we're going to take old batteries and directly make new batteries from that. And I think that'll really help the economics and some of the environmental issues. So again, just to remind you, I think some of the strategies to address these resource limitations that certainly we need to think about new extraction technologies, in particular for lithium, which I don't think we're going to get around. New battery concepts, I think, have an important role to play, while that may be longer term. And really today, we need to be thinking about how we're going to scale recycling to what it needs to be when half the fleet is in EV and that fleet starts coming off the market. And I don't know that people are going to want to plug them in as second use on the house. I think people are just going to take those batteries and make new high-performance batteries. And so let's start thinking about that. So, again, thank you all. Specifically, want to thank some great collaborators, and I highlighted work in particular of 3 of the students and a research professor that I work with, and the agencies that make this possible. So, thank you all for your attention. Thank you so much.
Quick questions for Paul?
Prologium, that's actually in production producing solid electrolyte batteries in Taiwan?
Promodium?
Prologium.
No, I'll
It's
check
worth
with
looking at. They were just qualified for use in the next generation of cars from Mercedes.
Okay.
And I believe they're also used in a Korean car. So
okay.
Worth looking at, very interesting.
Thank you.
And I've tested the batteries and they're quite interesting.
Okay. Our second speaker is Professor David Nickel. David is the Herman DeCamp Chair and Professor of Engineering in Electrical and Computer Engineering here at Illinois. He is the director of the Information Trust Institute, which for nearly 20 years has provided national leadership in the cybersecurity and resiliency of critical infrastructures. So with that, I'll turn it over to David. And I'll let you know when you're at 20 minutes.
Oh, there will be no problem there. So Paul's a hard act to follow, and in part because he doesn't put ums in between his phrases, as you will find I do. And also, he's got way better pictures than I do. Oh, I do have scary bedtime stories about cybersecurity, but I don't know that I'll share them here. So I was happy when Phil asked me to give this talk, in part because it meant, well, you're going to go have to learn something, because I have to confess, I'm not an expert in cybersecurity in transportation systems. Been doing a lot of work in cybersecurity in a bunch of other domains. I said, well, good, let's go see what there is to learn about this. And so I learned some stuff, and I will share that with you. So the executive summary, since we have a bunch of high-end folks here and you like to have things sort of boiled down and distilled, The risks that I want to talk about with cybersecurity and privacy basically come from exposure. Because we want to sound scary, we talk about exposure as being an attack surface, and that's really the places where an adversary can get a hook into things, hence an attack surface. But what's unique, I think, or different about electric vehicle infrastructure is the exposure, but also the physicality of the exposure. And what do I mean by that? Can compare that with the exposure, say, of wireless. A lot of people concerned, as they ought to be, about cybersecurity when you have wireless networks, and that's exposed, right? You go to Starbucks or someplace, and you have to be concerned. And by the way, when you go to Starbucks, please pop up what's called a VPN, so that people aren't eavesdropping on you. But you know, it's exposed, and that's going to be the case with vehicles, only more so, in large part because of all of the infrastructure that is there for charging. Has to be. And so because there's all of this infrastructure that's exposed, then that's going to give adversaries an easier way to get in. There's a risk not only to the infrastructure, but to the electric vehicle infrastructure, but to the electric grid itself, because the vehicle infrastructure will be a very significant component of it. And even as one talks about using parking lots full of electric vehicles as batteries and have them integrated somehow into the grid, you know, you're now talking about a major chunk of the grid that's interacting with this thing that comes from who knows where and interacts with it in who knows how. I mean, certainly one designs it to work certain ways and does everything you can to protect the interaction to work a certain way. But experience with complex systems is that they're complex systems, hence there are mistakes that are made in the design and in the protocols, and because of these mistakes, then there are ways of befouling things. So again, there's a bunch of exposed stuff out there. Credit card sales are exposed, wireless is exposed, but with the vehicle infrastructure, you have the physical piece of it that's exposed, and furthermore, damage can be done to the physical infrastructure. So that's all things to be aware of. Helpful, I think, to view some of these risks through the lens of some use cases. So one of those use cases would be the simple thing of charging for use. Now you can have your vehicle at home and charge it through your home, and you would say, well, that's pretty safe, until you realize that, well, there are home networks, and the homes are a vehicle, or yeah, I don't want to use the word vehicle. The homes are a pathway for adversaries to get into the networks that are in the homes and potentially interact with the system through networks and so on. I'm not going to worry about that a great deal. The home is probably one of the safer places to be, but nevertheless, the chance exists. You have the charging when you go through a public station, like the Tesla stations that you can go in and plug and go. So there's some kind of interface with them. They're out, and people can see what others do there, and they are relatively few, but nevertheless they are exposed. And when you're paying for things, then through those kinds of terminals, you are the system is dependent on the software that's there presented for doing the interaction. So now we've raised the ante so much, a notch for doing the paying part of it. So now there has to be some kind of interaction, be it credit cards or however it works, right? There's going to be some kind of interaction. More interesting one would be when you have a vehicle that's at rest someplace and it's getting charged. A variety of ways that the enumeration for using or for gathering a charge might happen, all of them involving software, all of them involving some complexity, therefore all of them having some kind of risk to being befouled by cyber opponents. There are also some privacy issues with paying for public charging. It gets involved now with geolocation information. Now, I'm not going to worry a great deal about this, in part because there are a lot of security concerns, and I don't think it's really so much a technical concern as it is a policy concern. Nevertheless, the gathering of information with the electric vehicles as they charge, as they interact with the infrastructure, other places, other ways, is going to link people to locations and time, as does your cell phone, and will be information that is governed by certain privacy rules, as is the information on your cell phone. And so from a technical point of view, there's nothing, really new there. However, it does mean that those that have the information, and now we're talking about electric utilities, are going to have to do things they haven't done before. And so it's going to be some kind of a burden on them just to come up to speed on what it is that they have to do. I mean, you could look at what happened in medicine when the HIPAA laws came along. And so now they all have to be very, very careful about the way that they handle information. There's something that's called the General Data Protection Regulation, which governs privacy in Europe. It's a standard that some are trying to deal with here as well. And there, that regulation requires consent by users for the use of that data. So all that means that there's an extra layer of friction that's going to be happening because of the data management. And there is, of course, increased opportunities for fraud. One of the models for charging is, charge to the vehicle. You pull your vehicle into a lot and connect it up, and there's some kind of thing that happens. But whatever's happening is happening electronically. There's some identity that's being exchanged, and there's opportunity there for spoofing. And so you can imagine that the bad guys would like to find ways of getting their vehicles charged without paying for it. Another use case has to do with the charging infrastructure. And here in the putting credit where credit is due department, I need to point to some work that's been done at Sandia National Labs over the course of the last 4 years. I sit on some advisory boards at Sandia, so I've been hearing about this work for a while. And so when I took this job, I said, I got to go look up that Sandia work. And I did. And there's a useful paper here. I've got the reference there, and it can be found if anybody's really interested in. But what they have done is they've looked at cybersecurity issues in the charging infrastructure and a variety of different points. And these are not just theoretical vulnerabilities. Anything that appears in that paper, they point to say, this has been seen, and they cite a chapter and verse. Not necessarily in the infrastructure, but the vulnerabilities themselves that they cite are things that are real, not just imaginary, they're real. And so that should be some kind of concern. They identify 4 points where there are cybersecurity concerns. And I'll talk to each of these in turn, but the 4 points, one of them has to do with where you plug the car in, where you couple it with the system. So there's going to be some cyber stuff that happens there. There's going to be the point where the user, the charger, is going to be authenticating themselves or their vehicle with the infrastructure so that everybody thinks it's on the up and up and the charging can happen, the paying for it part can happen correctly. There'll be a piece of this where there's information about the system that is translated or transmitted to some kind of services, data services that are gathering that kind of information about what's going on in the infrastructure and doing something with it. And then the last piece is that there in the bowels of the system itself, you have a lot of circuit boards that are chattering away with each other, and they have particular kinds of protocols that they use, and there are vulnerabilities involved in those, and as well as the access. So I want to touch on each of these 4 areas individually. So if you look at the connectors themselves, there are a variety of devices and a variety of protocols that are used in that. So is the diversity a good thing or a bad thing? Well, If you have lots and lots of means of doing it and lots of protocols, if one gets broken, the other ones don't. On the other hand, one of the greatest challenges in electronic voting systems and getting the software right for electronic voting systems is the number of different laws there are in different states and localities for this and that and the other thing. And so they do things different ways. That means that the software gets complex because of all these special cases. So this is clearly a place where there's exposure. The communication protocols that are used right now between the vehicle and the infrastructure are typically not protected. They can be protected. They ought to be protected. They will be protected, but right now they basically won't be protected. I'm reminded of an incident that was in the news. It was a big deal at one of the security conferences some years ago where there was a hack to a car. And everybody said, oh, because cars are very complex entities. There are all kinds of systems inside of the cars, and the systems are chattering away with each other. And there was a demonstration how if how did it go? If the CD drive was compromised, or the system was compromised, you could have the CD drive telling the accelerator pedal, to go to the floor and don't move. Say, well, that's pretty stupid. What accelerator pedal would listen to a CD drive? And well, there was no software to protect that because everything was trusted. So what the accelerator saw was a command to do something. So it did it. There was no authentication, there was no protection. And that's typically what happens when new technology is rolled out and integrated in things like this, is security is not one of the first things that's brought into the system. And because of these things, it needs to be. The kinds of bad things that can happen when the car interacts with the infrastructure, it could be that there are falsified information that's passed between them. Most of you will have chargers for your phones or your tablets, and a lot of them these days are so-called smart chargers. That's because there's some intelligence in the charger, there's some intelligence in the computer. You kind of cook them up, and there's some kind of interaction that has between them. So you figure out what the electronics looks like and go with that. Well, just imagine if those could be befouled somehow. A lot of that's analog, a lot of it is digital. And so if it's digital, then it's really subject to being befouled. And so you can imagine that those things get changed, then bad things can happen to equipment on either side of the connection. Another thing that is critical here, I think, is that the malware can be driven up to the charging station in the vehicle. So, the same car that's in the charging station every now and then gets taken to the dealership and brought back into the garage for various kind of maintenance. And what do they do in the garage? Well, they pop off the cover on a plug and they jam in something on their analyzers. And that's like using a shared toothbrush, and that analyzer, it could have been compromised by some other car, and other cars plug in and in it goes. So you can imagine now of having a number of cars that are carrying malware around and then connecting them to this infrastructure. So the concern there is really of widespread coordinated infection. A lot of the work that I've done has been in cybersecurity and the electric power grid, and it's correct to think that, well, if cyber attacks looked like squirrels being fried or trees falling down and cutting off lines, then there's not a great big deal because systems are engineered to deal with that. Systems are not engineered to have half of the protector devices be compromised by the same firmware attack to all do something in concert at 12 o'clock high, right? So it's these kinds of attacks that don't happen naturally and haven't been anticipated that can really cause bad things to happen there and here as well. Okay, anybody scared yet? No? Okay, well, we'll keep going. The authentication piece of that, we have authentication of the user to the infrastructure, and they'll use RFID tags, or they'll use their cell phones with NFA or credit cards or some kind of terminal input. It's possible. There's a lot of talk now about so-called plug and play. So you connect the car to the infrastructure, and the authentication is happening through using that cable as a network and causing the interaction to have. So that makes things really simple in one way, simple for the user. It does not make it simple for the system, because to do authentication, you have to really do authentication in a cryptographic sort of way. And there's a whole infrastructure for doing that that's called public key infrastructure. And well-developed, well-studied, usually works, also fragile. Different things can happen and cause that infrastructure to fail. So it's very easy to imagine when you have vehicles that depend on this infrastructure for managing security through PKI, to have something happen in the internet and have PKI be broken. And so now all of a sudden you've got nothing. You connect your car, well, they can't authenticate, so you've got nothing. This is possible. Told you I was going to have some none. The user interface between the user and the system is a significant attack vector. It's going to be using either standard software that a lot of people know about, a lot of people have studied, may have some flaws in it, and those flaws can be exploited, or it might be homegrown software by a company, and if it's homegrown software by a company, chances are that there's going to be some flaws in it, unless they've gone through what turns out to be extraordinary effort to really harden that stuff, which doesn't frequently happen. The interfaces here tend to be complex, and because of this complexity, I think I've said this before, there's an echo in here. Because of the complexity, that means that mistakes can be made in the protocols and the interfaces, and that allows the adversaries to get in. What would happen if this did occur? It could be that access is denied to particular customers. I've seen things about how one can attack cellular systems. So if you want to cut off a particular person who has a particular cell phone, that can be done in a very selective sort of way. Same is true here. You could, through malware, deny service if you wanted to some particular person if you got into the bowels of the system and knew enough. Could bypass authentication altogether, so just roll on up and charge, or could just disable charging altogether for everybody, or change the prices. So there's, confusion that can happen if that were to be messed with. If you look at the interface with the internet, they will typically use web servers. These web servers are pieces of software that are frequently studied very hard by adversaries to find holes in them. They are also pieces of software that turn up in the craziest places, such as in the middle of a control station for an electric power grid. And you say, well, what on earth is a web server doing on this device right here that's sort of gathering information? Well, it got put there because it has infrastructure, it has capability of sharing information with other devices. And so the manufacturers don't have to rewrite that software, they'll just jam Apache in there and it can do that stuff. And that is true, but it also means that you've put in a lot more capability in places that's not really needed and created more ways in for the adversary. The compromise could lead to manipulation of the infrastructure from the internet, easy to imagine. That also, if the adversary were to gain control of a large number of the devices, they're going to have the power to impact the power grid, the transportation, and other critical infrastructures that depend on all of this. The maintenance interface, and this is really where the Sandia people get excited because this is the kind of thing that they do, is they look at the devices, they look at the circuit boards, they look at the interfaces between the circuit boards, and there they are using communication protocols, using from a variety of ways, and they are guaranteed to be unsecured. There are connections that are made. You can have USB plugs to interact with these devices. You can have them chatting over Ethernet, and almost surely that communication is not going to be protected. You can use something that's called a JTAG, which is a hardware way of connecting to a board and communicating with it and getting things off of it. So again, if the adversary had physical access to the bowels of the infrastructure and these circuits that ran it, then they could do fairly seriously bad things. And they assert, Sendia asserts, that the connection points are often just sort of left open because, hey, they're secure, right? They're behind a locked door, or they're behind a chain link fence, or whatever it is. There's frequently an assumption that physical security is good enough, and frequently it is not. Okay, another case is so-called electric highway. There's a variety of technologies that are being researched where you can charge a car as you drive along a lane. Now, you probably can't see the tiny little phrase that it says, image courtesy of Highways England. You can probably tell that they all are driving on the wrong side of the road. But the point was this was too good a picture not to put on the slide because it suggests, what happens is the car drives along in a variety of ways that are being investigated to do this. And so there's going to be exposed communication of all kinds of things that are happening here. So all of the things that I have said about charging and the exposure, the physical exposure, they play out here as well. Summary, on time and under budget, I think. So, electrification. Well, it's certainly going to, is increasing societal dependence on complex cyber systems. We are already very dependent on complex cyber systems, so this is just raising the ante, so to speak. The electrification system itself depends on other critical infrastructures, like the electric grid, for example, or for that matter, the money side of it, authentication and billing. And so if those are befouled, then the electrification system could become befouled, and so our ability to travel can become befouled when we're dependent on electricity. The whole infrastructure is dependent on widespread, physically unprotected exposure that's coupled to the power grid. And so there's the risk. The electrification reduces the impediments that might exist for widespread coordination interference. Again, because of the exposure of the infrastructure, the many points, the possibility of doing things so that events could be caused to happen in coordination with each other. All of that means that there are risks associated with that. There are things I mentioned having to do with personal data, geolocation data. That's going to be something that companies will have to deal with. And so it may well be the case that the legislators will wake up and say, oh, cybersecurity for electrification, we have to have that. You have to give it to us. And that's policy. But the responsibility for actually doing that and the liability when there are failures, they're going to be driven, I think, by incidents and lawsuits and things like that. And so it'll be hashed out in the court who has to do what. And so I think it's going to be quite a time that's in our future. And this is just not with electrification. I mean, this is for all kinds of things involving cyber stuff. And we're starting to see some of this kind of thing emerge with cybersecurity and compromised data systems and so on. But, okay, with that, I am finished.
Time for maybe a quick question or two, and please wait till you get the microphone to ask your question.
Can I ask my question?
Yes.
So, sorry to offer you one last question too.
Microphone's coming, hold on.
So
totally agree with the, thank you. I totally agree with the risk of the coordinated attacks causing difficulties with the electric grid. It seems like there's one more opportunity with coordinated attacks, which is to the transportation system. I mean, if everybody's car does something bad all at once on the roads, it could be really dangerous. Just yet another avenue.
Oh yeah, no, absolutely. And I was tempted to follow another trail down another rabbit hole that has to do with smart transportation. It wasn't tied directly to electrification. But now as you get into systems where you've got cars talking to the infrastructure and all of that, there's a whole nother place where things can go bad.
You laid out all of the vulnerabilities very well. Any solutions? End-to-end encryption? What possible things should we be working on? Trying to protect ourselves.
The kinds of vulnerabilities that I pointed to were almost always limited in the sense of here are things that connect to each other. This is the way they connect to each other. Because these things can break, bad things can happen. That remains true, but it does not mean that we shrug and say, it's broken. I'll give you an example, only because I'm working on it, and that has to do with the fragility of the public key infrastructure. When I talked about authentication and how you need to have authentication on both sides. It's fragile. It's been demonstrated to be fragile, and so we're working on research that makes it more resilient. Won't go into the details, but say, there's a problem, we're academics, there's a problem, let's work on it. But a number of these things are not just academics working on it, there are companies working on it. So things will get better. Things will get better without question, or the known problems will be addressed and then new problems will emerge. That has just been the way of it, and will continue to be the way of it. I could go on about what needs to happen, but I won't.
All right, let's thank Dave.
All right, thank you.
I know I'm not going to look at my car quite the same. Our final speaker for today and today's symposium is Martin Eberhard. Martin is an alumnus of the University of Illinois, a veteran of Silicon Valley and entrepreneur, and an inventor. He was the founder of Tesla, its visionary, and was its CEO until 2007, just before the launch of the Tesla Roadster. In 2015, he was inducted into the University of Illinois Granger College of Engineering Hall of Fame. And this week, he is participating in the Illinois Leadership Center as their inaugural Leader in Residence. At 7 p.m. this evening, I'm going to give a little commercial for this, he will be a guest at the ILC, Illinois Leadership Center event in Lincoln Hall Theater on main campus. So you're welcome to attend that lecture as well. But let me bring Martin up here, and looking forward to this final talk.
Thanks very much. It's a couple of hard acts to follow here. All right, so I would like to tell you a little bit about why I think the future of transportation is electric in the context of what I've learned through my career doing EVs. And a quick agenda, I'd like to talk a little bit about well-to-wheel efficiency and comparing different fuel sources for vehicles, a bit about hydrogen fuels, some reasons why electric vehicles in the past didn't work and what we did differently. And then I'm going to touch briefly on subjects outside of my expertise, a little bit about long-haul freight and other kinds of trucks. I'm not going to talk about anything about autonomous, full self-driving stuff. I'm not going to talk about flying cars or any other aircraft. I'm not talking about any Hyperloop, any of that kind of stuff. So I'm trying to stay real here. All right. So this is a slide from my early presentation in 2005 for Tesla. And in this time, I argued that our concern about oil consumption, about fossil fuel consumption, was a concern for both sides of the political spectrum. And I put this slide up, basically saying that for the left at that time, global warming was real, and we were very concerned about it. For the right, it was national security and our dependence on foreign oil. And I would put this slide up and say, you probably relate to one of these images, and the other one pisses you off. And it doesn't really matter which one. They're both good reasons to buy electric vehicles. And I think that's still true. So with that in mind, the problem I set out to solve was this. There were, at the time, almost 1 billion cars in the world, and it was a prediction that we would be at soon 2.4 billion cars. And we couldn't possibly power all of these with oil. It's just not reasonable. I did not start off as an EV enthusiast. I started off as a not fossil fuels enthusiast only. And so I looked at every pathway I could think of to power a car. And for each of them, I did this. I looked at what is the resource consumption per kilometer, what is the well-to-wheel carbon footprint per kilometer. And of course, the conclusion I came to was that electric cars made by far the most sense. And I'll walk through a little bit of that thinking. Are they really better? So this is how I looked at it. So just looking at a gasoline car, in that time, 9 liters per 100 kilometers was a typical, reasonably good vehicle's fuel consumption. We know what is the efficiency of converting crude oil into gasoline, and you can compute then how much of energy that comes out of the ground does it take to drive that car per kilometer. And you can do the same thing for a pretty good electric car. Here's a Prius, roughly where it stands. Okay, so what about electric car? Let's just say I'm going to power my electric car. I know what its energy consumption is. I'm going to do it using a very old coal-fired power plant. This is a 20% or 29% efficient plant. I know what the efficiency of the grid is. I know what the charging efficiency is. And I come out with a number of how many watt hours of coal I'm going to consume per kilometer, right? And of course, with modern coal plants, it's better. This is a state-of-the-art combined cycle coal-fired power plant. It's better. And coal is, from an energy perspective, and certainly from a carbon perspective, possibly the worst way to make electricity. Much, much better is just natural gas. And at the top end of natural gas are these combined cycle plants like this one. So if you stack this up, what you see is that the very best we can do with a gasoline car has about the same footprint as about the worst we could do with an electric car. And if you try a little harder, you wind up with a much lower carbon footprint using electric vehicles. And I did this analysis with every kind of vehicle I could find. And of course, I don't need to power the car with fossil fuels at all if I don't want to. For example, there's my car, and that's my roof. And that roof powers my car and my house. So I don't buy gasoline, I don't buy electricity either. All right, I'm actually a little sad that we have to have this discussion about hydrogen in cars again. I thought this was a settled subject, but it's not. The appeal of hydrogen is that I use hydrogen in a fuel cell, my waste is just water, and it drives the car, and that's just great. And the question you have to ask is, where does the hydrogen come from? And as it turns out, there aren't any hydrogen mines. We have to make it. Well, that's not so bad. You just use electrolysis, which is just water, and you get hydrogen. It's perfect, right? But of course, water is not the real resource being consumed here. It's electricity. All right, and so you can look at the system and realize I'm putting electricity in one end. I do some electrolysis, I do some compression, I put it in a fuel cell, I get electricity back out again, and hydrogen is merely an energy carrier. So the question is, how good of an energy carrier? And efficiency matters, right? So I can compute electricity in and electricity out, and that's my efficiency. And it doesn't matter how I got the electricity. I can use it. I can use carbon fuels. I can otherwise use green energy. Either way, the efficiency matters. So, all right, so taking optimistic proposals for hydrogen, electrolysis at 70% efficient, we really can't do that yet, but that's a nice number. Compression, 40% efficiency on a fuel cell, that's a 20% efficient energy storage system. Compare that to a battery. A battery is on the order of 85, 90% efficient storage system. You go about 3 times as far on the same electricity with a battery electric vehicle. Or you would need 3 times the generating capacity to go the same distance, either way you look at it. So looking at a real-world example, here's a 2015 fuel cell vehicle from Hyundai, and we know what its specs are. They tell what it is, and you can calculate that, how much natural gas I would need, in this case using steam reforming to produce the hydrogen. And we know how far that will go, and we can calculate that vehicle consumes 16 kilometers per kilogram of natural gas. I can do the same thing with electric vehicle and run through the numbers, and if I just make the electricity with natural gas, I know what its energy consumption is. It's considerably less. So you see that the electric vehicle is using 1/3 the energy. Or much more interesting, I can compare, in the same year, Hyundai also made an electric car that was battery powered, and we can calculate its energy consumption. It's again, it goes 3 times as far on the same amount of energy. All right, so back to my conclusion is that electric cars were by far the best choice, and I'm willing to concede this is assuming that we think that cars make sense at all, and I think it's perfectly reasonable to say, should we be even having cars in an urban environment, or is there a better way to move people? And that's for a different discussion. All right, so with that as the background, in 2003, all of the car companies that had been making electric cars had quit. There were no electric cars for sale anywhere in the world. And the reason was this: the electric cars that people had thought about were not selling. Nobody wanted them. These were cars that didn't appeal to the people who were buying cars, right? They didn't appeal. Appealing cars were something different. I mean, maybe we didn't all go out and buy a Corvette, but we certainly, that's our vision of what a car ought to be. It wasn't those fiberglass bodies on golf carts, right? Sorry about the politically incorrect slide. EVs were not sexy. And so with this in mind, the number one radical idea behind the start of Tesla was to revive the EV by making an actually sexy electric car. And that then led us to consider technologies that would not have otherwise been available trying to hit a low price point car. And the first of those was to fix the range problem by using lithium-ion batteries. And today, 100% of all electric cars, of course, are using lithium-ion batteries. But at the time, I was told by people in the auto industry that lithium-ion batteries would never be used in cars. Right? And in fact, this was really was the one item I had to prove to myself before I could even start the company. Could I build a system, in this case with nearly 7,000 lithium-ion cells in it, and control it? I understood already lithium-ion batteries from previous work, and I understood what it took to manage that kind of battery system. And the question was, could I scale that kind of management up to this kind of battery pack? And the answer was yes. And then maybe a somewhat radical idea at the time was to use induction machines instead of permanent magnet motors for a lot of good reasons, and that's just as a background where the name Tesla came from. And it worked. In 2008, we launched the Tesla Roadster. It outperformed pretty much every other car on the road and had a range that was triple what anybody else had ever had. What it did was it launched the first successful new American car company in a century. So it worked. This is actually near my house, and that car on the right side is my car. That's the second Tesla ever made. And the rest of them are a bunch of people that came out for a rally for these Roadsters not too long ago. So in 2003, the electric car was declared dead, and in the same year, we incorporated Tesla Motors to revive the electric car. By 2017, all major OEMs were now selling electric cars again, from zero to all of them. And today, we're very, very close to price parity. I think we're within 3 or 4 years of, at least in some of the major market segments, seeing the electric car being the same price as the equivalent gasoline car, right? So now I'd like to touch on long-haul trucks just for a moment. I'm not an expert on this, but I've thought about this a bit, and in fact, I took a class here from a professor who's, I think, retired now, Professor Hannon. We looked at the efficiency of moving freight by truck versus by rail, and it's a 7-to-1 ratio. I mean, it's radically more efficient to do that. And I expect that kind of efficiency ratio will be true for electric vehicles as well. I don't see any reason why it would be any different, because it has more to do with rolling resistance and aerodynamics than anything else. And so the question is, why is trucking cheaper here? Why do we move our freight on trucks instead of rail? And what we learned in Dr. Hannah's class was that it's an infrastructure problem, that the road and waterway infrastructures are paid for by us taxpayers, but the rail are not. And for that reason, it works out to be cheaper for the shipper to move stuff by truck. And that's a hard problem to solve, for sure. But with a 7-to-1 efficiency ratio, it just seems like we should figure out how to solve that, even if it's expensive. All right. Delivery trucks are a different case. I've looked at this quite a bit, and I actually have been struggling to understand why nobody's cracked this nut yet. And I think they have now, just now. Delivery trucks typically have a very fixed route. if you're running a diesel engine, it spends a lot of its time idling, which is just bad. And these seem to be ideally suited for electrification. And finally, both Rivian making delivery trucks for Amazon and some others making them for UPS and others, I think we're going to see this sooner rather than later. Okay, so back to my original slide here from 2005, just to wind things up. I mean, this is the same slide, just different pictures. If ever was obvious, it's obvious that global warming is real now. I don't think we have to argue about that much anymore. And our dependence on oil from countries where they don't really like us very much is dangerous here and every place else in the world. And so, yeah, so for increasingly obvious reasons, I think we have to break our fossil fuels addiction. All right, so I'd say thanks very much. You guys are a tough crowd.
I know it's late. We're close to the reception. One in the back.
Terrific presentation. Thanks so much. I was wondering, when you were developing the car, were you also thinking about the infrastructure? And is the Tesla supercharging infrastructure a result of your work?
So were we thinking about the infrastructure? Yes, in a funny way. People think of it as a chicken and egg problem, but in a way it wasn't already. Somebody had already laid an egg. I mean, there was electric services distributed all over the country, and in the early days, you could just plug your Tesla into an electrical outlet. You'd look for a 220 outlet if you wanted to charge quickly, but that's what we did. So on that front, yes. The supercharging structure, I had nothing to do with that other than we knew that was what we had to do next. But, you know, an early stage startup company is a little bit like, I'm going to insult a little bit here, like the junior high school hockey team. The puck is over there, and everybody's over there whacking at the puck, and there's nobody watching the goal or anything, because you can't. You just don't have enough people to do that. And it took a while for Tesla to grow up big enough to be able to do additional things like, for example, supercharging infrastructure. One more point on the supercharging infrastructure. I would say the superchargers are useful if you're doing a long-distance trip, which we typically don't do very often, once or twice a year. The real purpose of the supercharging infrastructure for Tesla is twofold. First of all, it's an objection eliminator for people who have never owned an EV. And they think, oh, yes, I can get on the supercharger, I can make it to wherever I want to make it to, whether or not they actually do it. But it gets them over the hump. And the second thing is fantastic advertising, that these supercharging stations are in places where people see them, and people say, Tesla, 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 and they buy the car. So in a way, that is actually more important than the actual supercharging.
I'm just curious, in one of your comments you mentioned about the idea if we should even use cars at all. And what are your thoughts on just personal small mobility devices within like 5-10 miles?
Yeah, I mean, I guess I spent enough time in San Francisco and other big cities to realize that if the cars were electric or autonomous or even flying, it's going to be a traffic jam anyways. It'll just be a different kind of traffic. It doesn't solve the problem. So I don't have a good idea myself about what the answer is. I've looked at these micro-mobility with scooters and things, and I've also known people who have gotten really hurt on those things. I mean, there's a lot to be said for having some metal around you. I ran into some guys that had an idea for a startup company that I thought was interesting, which was to basically take the underground infrastructure of major cities like London or Paris and bring some 21st century technology to that. So instead of a long train that stops at every single station, their idea was pods that would ride on the same infrastructure, the same tracks, but would be programmed to take you directly to your destination using an app and some intelligence, and maybe some more places for the tracks to cross each other. I thought that's maybe the right direction, you know, to get the majority of the traffic off the street. Yeah.
Good question. So thank you for being here. Thank you for everything you've done. I know you said you won't talk about flying, but just what are your thoughts on what, in terms of electrification of aircrafts of different sizes?
Again, it's a bit outside my field, but what I understand about aircraft in general is that the amount of energy you need to make it a reasonable trip is a lot higher, and today's batteries just don't have anything like the energy density you need. So my feeling is that if we want to get away from carbon fuels in aircraft, it's either going to be perhaps hydrogen or, I think more likely, some synthetic fuel that may be made from some green source. And the reason I say that is that the energy density of a liquid fuel will be a lot better than a gaseous hydrogen.
Hi. You touched upon trucking a little bit, and I wanted to ask if the hydrogen versus battery argument that you made would still hold in that context, yeah, especially because hydrogen is still being considered a pretty attractive option for long-haul trucking.
Yeah, okay, so my concern about hydrogen really has to do with the carbon footprint of it. I mean, you know, if I produce hydrogen and then turn that back into electricity in a truck, it's a 20% efficient system. And if I can do it with batteries, it's more like 90%, maybe 80%, somewhere in there. It's radically more efficient system. So in any case where I can make the batteries work, I would rather do that. But I mean, I argue for long distance freight that it ought to actually be on rail, and batteries either shouldn't exist or should be fairly minimal on the trains, because we can do overhead wires like it's done in Europe and even some places here in the US.
I think I'm next on the question. Thanks again for speaking today. And the question I have for you, Martin, is I'm wondering if you've seen Toyota's latest talking points on hybrid versus battery electric, where they've taken into account the life cycle analysis of the batteries and the CO2e from production of the batteries. And their argument is basically that building, say, 10 hybrid cars has quite a bit more benefit to society than building one battery electric car, because you're using the same batteries over a broader number of vehicles, and the total LCA gives you more net benefit than battery electric. Have you seen the write-up? And I'd like your comment on it if you could.
The answer is no, I have not seen the recent argument, but I've been listening to Toyota making arguments about why not to make electric vehicles for decades now. And you know, they used to tell me that hydrogen was the way to go. They were the last of the major car companies to go on hydrogen. So I don't know quite what to make of their research on that. As far as hybrids go, I mean, to me, a hybrid, especially not a plug-in hybrid, but just a hybrid, is just another way to make your gasoline car more efficient. And that's great. You should do that, just like fuel injection and all the other things we've done to make the cars better. If we're going to burn fossil fuel, burn it intelligently. But it's not the same thing as getting off of the carbon. So, yeah. I used to have a bumper sticker on my car that says, when you drive in your Prius, you're still driving with Osama bin Laden.
And I guess a follow-up question, have you followed any of the research in synthetic e-fuels and kind of the rebirth of the ICE concept to use closed-loop carbon fuels?
So only externally, only lightly, and my interest isn't in that case because it's not very efficient, but for aircraft, because I think that synthetic fuels like that, at least for now, that's the only way I can think of making commercial aircraft have a better carbon footprint.
Thank you.
Thanks.
There's an idea about, you know, the battery and charge and everything, idea circle around, that is the battery swap approach.
Yep.
And you have car, but you don't need to have own the battery pack. And whenever you need to charge, you just, you know, bring your used up one and then get the new one from a gas station or something like that. I think it's a good idea because it solves the conflict between the driver versus the charge time and charge station. You can get your battery very quickly, and then charge station can, you know, charge the battery in a more reasonable way and then fit into the power grid very well. That's what I'm thinking. Another one is the battery can be controlled by the gas station, or in this case, in the charge station. You know, what is the time to retire the old one? What is the time to burn the newer one? I think it's a good idea. I just want to see your comments, opinions, and is it possible, good way?
So I've been looking at battery swapping since the very beginning. Do any of you remember a company that came along, an Israeli company called Project Better Place? Yeah, so that was their business model. And the interesting thing was, before the founder of that company, Shai Agassi, started the company, he came and visited me at Tesla, and we went through a spreadsheet analysis of the costs on that very carefully, and we could not come up with any model where the economics worked, and yet he started the company. So there's at least two fundamental problems with battery swapping. The first is that it's just inescapable for the near future that the battery is by far the most expensive component in the car. I mean, it dominates the price of the car. It might be as much as a third of the price of the entire vehicle. In a swapping environment, I need to have more batteries than I have cars. I got to have more or less one on the charger too. So I've just taken the most expensive part of the car and made it more expensive. The costs don't work. Okay, that's the first one. The second thing is that you're either going to have to carry a lot of different kinds of battery, or you're going to have to force the industry to standardize on a single kind of battery. Otherwise, it's just unmanageable, right? And today, I mean, standardization is the exact opposite of evolution. Standardization says we're going to stop evolution, now this is what we're going to make. Today, batteries are still not good enough, and we want that evolution to run as fast as possible. That's evolution in chemistry, evolution in voltage, evolution in form factor, evolution in cooling, evolution in safety, everything. We want that to run. It's not the time for standardization anyway. So these are my two biggest concerns on that. The other side of the coin is that most of the time when I hear this concern, it's from people who haven't actually lived with an electric vehicle, that at least for those of us who are able to have a charger at home, which is most EV owners now, charging is just not a big deal. It takes just a few seconds to put my connector when I get home. I read that I think Hyundai is now developing a robot to plug that into your car. I'm serious, yeah. And it's like, why didn't they do it for the gas pump too? You know? Yeah.
Yes, thank you.
Thank you.
So Martin, why didn't we start with the cars that have the line cord and the flap, and I just pull the line cord out like I do my appliance at home and plug it in the wall? Why do I have this stupid cord I have to deal with?
Well, so there's a couple of reasons for that. What's inside of a charger is not much, actually. What's inside of a charger is some mandatory safety equipment, a ground fault circuit interrupter. In the case of Tesla, we had a circuit that would detect if you yank the cord. So if somebody catches on or if you drive off with it. And then a small circuit that tells the car what is the maximum charge rate they can run. Before Tesla came out with their mobile charger, I personally made them at home and sold them to 20 or 30 Roadster owners. I made them myself in my garage. The total cost was $20. You know, the most expensive part was the connectors and the wire. That's where the money is. I know that you've been looking at charging it with 110 volt outlets. I would argue that for the same exact cost of wiring, you might as well do 220 and run charges twice as fast. But in some sense, you're right that the Tesla Roadster was designed so it can charge at 70 amps, which allows you to charge the whole car in a couple hours. It's pretty quick. But in reality, we charge overnight, and you can get away with 20 amps is just fine to charge a car. I've got my wife's car set up to charge at 30 amps because the battery lasts longer if you charge slowly. So yeah, part of it is perception again, that early on we want to say, yes, you can charge quickly if you want to.
I get the last question as an academic. What I'd like to ask in an academic institution hosted meeting, how do you think the curriculum should evolve in subjects like thermodynamics? We at Illinois and most Big Ten plus schools teach few thermodynamics classes, and based on your presentation as well as your experience in the real world that you referred to, how do you feel these subjects should evolve?
Well, one of the things that I've admired at this university since my time has been the inclination to do cross-discipline education, to learn combining this field with that field. And I think that thermodynamics combined with electrical engineering and thinking about the thermodynamics of your motor or whatever, these kind of fields I think are good, and more of that is better. I mean, this is kind of how I think about it. It's when I was here, it was much more common to be teaching each of these subjects in silos. And I see a lot more now of blended education and learning how to use these different fields together to solve these problems. I'm not sure if I've really answered your question, but that's kind of what I would suggest.
Great answer. Thank you.
Thanks.
I'd like to thank all three of our speakers. I'd also like to add that in material science in our graduate program, we have one required course that graduate students have to take, and it's thermodynamics. And then they're free to mix and match across many disciplines in their graduate education. So I think thermo remains important. Let me invite you all to the reception that is just outside these doors, and you're welcome to continue discussing with our three speakers. So let's thank those three speakers again for just doing a fantastic job. And I'll also remind you that you can spend the evening with Martin at the ILC, the 7 p.m. event in Lincoln Hall. So thanks, everyone.